and I'm going to turn it over to Doug Knabe. We're going to show his presentation from my local, and then he's just going to tell me when to advance the slides. So, Doug, tell us who you are and take over.
Sure. Thanks, Jim. Yeah, I'm Doug Knabe, KN5DK. Let's see. I've been licensed since 1964, originally WN0RCD way back when. And I'm an electrical engineer. I've got a bachelor's and master's from South Dakota State University, and I worked at Texas Instruments for about 35 years. And then I worked a startup after that in kind of the solar or alternative energy field, and that's where I ran into SMA inverters and so on. Anyway, that's my background. I appreciate your asking me back. So the last presentation was in December, and I had 45 kilowatt hours of LFP batteries online running my house, and I've since added another 15 kilowatt hours, so I've got about 60 kilowatt hours of battery storage online for the house. So this is an update on all of that, and why don't you go to the next slide? So I conceived of this whole house UPS thing way back in October of 2022. My wife was in Germany and I had time on my hands. And so I thought, well, why don't energy prices are getting more expensive and TXU keeps advertising free nights and weekends. Why don't I take advantage of it? So I came up with this plan, and but it is expensive, and some might say it's a dubious return on investment. But a lot of times you run into 90% of everything is crap, Sturgeon's law. So anyway, next slide. So this is the original timeline for the project. It started in October of 2022. It took, I didn't take long to get some Sunny Island inverters. These inverters were what I had used in 2011 at the startup, and I just bought some used ones off of eBay. I think they range now anywhere from 1,000 to I don't know, $1,500 or $2,000 a piece, depending on time frame. And and then I ordered some LFP lithium ion phosphate batteries in October as well. And those took a while to arrive from China. They got in January of 2023. So then I did a bunch of construction, and by the time I got to towards the summer of 2023, I had the house running off grid except at night when the batteries were charging. But I still was in a constant rate plan where I paid, I don't know, 14 cents a kilowatt hour, so that the system didn't help me. And finally, well, let's see. I think I had some issues with starting my air conditioners, and I ordered a couple of super caps. I have something like 260 farads in parallel with the DC bus to stabilize and work through the startup surge current on my compressors. And so I got those installed. And then by May of last year, I switched to the TXU free nights and quote solar days plan. And things have been going pretty well. But we'll get into a lot more details after that. So next slide.
I'm not seeing slides. Is everybody else seeing slides?
Yep, looking great on this
Yep.
end here.
Okay.
Go ahead, Doug.
Okay. Okay. Basically, here's a list of my initial naive assumptions when I started the project. And it sort of goes along with too soon old, too late smart saying. Um, my initial understanding of the code was that batteries under 60 volts are class two and the code doesn't care about them. Well, that's false because class two is under 100 VA of power, and batteries are an energy storage system. And actually, since 2017, they drew up this code UL 9540, which is a very extensive spec about battery storage systems. And so basically, that sort of obsoleted a whole bunch of technology, I think, including the SMA inverters that I worked with and used. Um, the next assumption was that LFP battery packs with 400 amp, 52 volts is sufficient to start the house. The issue is surge currents, and for example, I have a 5 ton, I have a 5 ton and a 4 ton compressor, and when those start up, I can see 150 amps at 240 volt. Surge current. And so if you translate that down to 52 volts, that's a lot of current. And so that took a while to work through. And then I didn't really understand inspections. And so basically, I've been doing all my electrical work just using standard electrical components. And but apparently, to do it right, you need to go get code and submit a plan and all that kind of stuff. Well, I didn't do that. So that's a problem. And the other thing is you can manage the system when you're out of town. Well, that's partly false. Last summer, I couldn't tell the difference between a house failure and an internet failure. Last I think July or whatever, we were in Europe, and I was monitoring the house from Europe, and I couldn't get access to it, and I assumed that that meant the house power was down. Well, it really wasn't. It was just the internet was down, and what had happened is the copper thieves had cut the old copper lines in that were overhead in my neighborhood, and the copper lines or the fiber lines, which I have now, were in parallel with the copper. So when they took the copper down, they took the fiber down, and everything went bad. But now, actually, it's been pretty reliable since they've gotten rid of all of the copper that runs parallel with the fiber optics. And then the other thing that I had to work through is battery packs in parallel just work. Well, that's false. You understand that when you put things in parallel, especially batteries, there's lots of issues with current sharing as well as the battery management system, state of charge calibration, and so on. So I'll give you an update on that. And then, of course, my last naive assumption is salesmen are honest, and that's false by inspection. I ran into that, and we'll get into that later, but I ran into that when I was looking at the Chinese batteries. And basically, they said they'll supply you 100 amps continuous and 200 amps peak. Well, I had assumed that, and it wasn't until I was able to get into the management software that I found that the batteries were set at 110 amps, and that would alarm out and stop my inverter. So it took a while to work through that. Next slide. There we go. Okay, so what I'm gonna do is I've kind of reorganized the presentation, and the first thing I'll do is show you the some overview of the SMA Solar Academy in Germany. And I visited that. I didn't actually take the classes, but we visited the facility in Kassel, Germany in December of 2010. And in that section, I'll give you the an inverter tutorial and all that kind of stuff. The next section will be basically the LFP batteries that I got from China, RJ Lithium, and talk about some characteristics of those. And then I have a new section of do-it-yourself 15 kilowatt hour LFP construction and what it takes to do all of that. And then lastly, if we have time and if there's any interest, I listed a bunch of energy storage system standards and some important things that are in those. So next slide. Okay, here's the solar. Next slide again.
Hang on, something's wrong.
Okay.
Are we caught up now?
Yeah, right. That's perfect. Okay, so I guess I alluded to the fact, why did I choose SMA inverters? There's a number of different ones, but I chose SMA because I felt that an AC coupled multi-mode system was give you the best flexibility, and we'll get into that a little later. Plus, SMA was the largest German solar inverter manufacturer. They're a pretty big company, about 2 billion in sales, and the inverters are known for being bulletproof. And I'll show you the specs and why a little later. And I was familiar with the first gen capability of SMA inverters from my startup work in 2010 to 2012. Next slide. So this is a view of the Solar Academy, and they're actually in a suburb of Kassel, Germany. Very beautiful section of Germany. The Solar Academy is on a kind of a elevated building, and they've got solar panels on top and a whole ton of inverters in the main lobby and so on. So I think you can take classes there, and it's pretty good. Next slide. Here's the top view, courtesy of Google Maps of their facility. You can see the solar panels on top of their building. They also have quite a number of two-axis solar panels that they use to demonstrate different capabilities. Next slide. So this is the drive into the academy, shows a solar panel array on a pole. Next slide. This is a little more detailed view. You can see they have an anemometer at the top and probably lightning rods also at the very top, built on a very robust pedestal. Next slide. Here's the back view of that panel. So they're actually doing sun tracking because they can tilt and rotate. And by being able to do that, you generate somewhere between 40 to 5 to 50% more power output per year by tracking the sun than you can get with fixed panels. Of course, they got lightning protection. There's that anemometer on the top. They probably have about 7 kW of capability in there, and that red thing in the solid red thing is the Sunny Boy inverter, which is good for about 7 kilowatts. Next slide. There's a number of different types of inverters. So there are grid tie and off-grid and hybrid inverters. And it's real important to have anti-islanding capability on your inverters. What anti-islanding really is when your grid power goes down, you don't want to be pumping power into the grid because the lineman that comes out to fix the transformer or whatever that blew is going to potentially be electrocuted by your solar panel or your inverter driving power into the grid. So that's really important to do that. And then the last bullet here is frequency shift power control as a means of controlling the power output of solar inverters in an AC coupled system. Next slide. So a grid-tied solar inverter, which a lot of people have in, all over the country, they're permanently connected to the utility grid. They convert DC to AC with the grid frequency and voltage, and they shut down when the grid goes down to protect the grid lineman. So you think you've got solar panel, but if you just have a grid-tied solar system, if the grid goes down, you're down. There are some, and actually SMA makes inverters that have maybe one panel dedicated to a single power outlet, so you can get a little bit of power off the solar panel. But the main solar that you run your house with has to shut down when the grid shuts down. Uh, then there's off-grid solar inverters, and of course, this is part of a standalone system. They're typically paired with battery storage and used in remote locations to provide energy. And then the type that I have is the hybrid solar. Well, actually, I don't have that. The hybrid solar inverters, they combine the functionality of grid tied and off grid. So those will feed energy into the grid, store it in batteries, and provide backup power during outages, which is what I have. But it allows energy independence while still being connected to the grid. Next slide. So SMA's current products are, they make PV modules, photovoltaic modules. I think there's several different techniques of converting the DC that you get off of a solar panel into AC, and SMA makes that. The other, they've migrated their inverter strategy to a combined, basically combined battery inverter, which is what I'm using, and a solar inverter. And so that they call it a smart energy system that does multiple units. And the SMA doesn't generally sell the battery system. But I guess they work closely with BYD, which you've probably heard is a large Chinese manufacturer of batteries. And they make battery boxes anywhere from, I don't know, 12 to 30 or more kilowatt hours. And on those battery systems are also UL 9540, which is the new fire protection spec that's in place in the U.S. And then, of course, it's important to monitor everything, and SMA Energy app lets you do that. I have one on my phone and monitors the system. Next slide. So this is an overview of first gen capability of SMA. Overview of this is basically the Sunny Island inverter in blue there it's a bidirectional inverter that allows current to go either direction, either to charge the DC batteries or to power the loads. And then it allows a grid connection. And then there's a separate bus for the load connection. The secondary panel connects to the critical loads. And then on that protected load bus, you can also connect a Sunny Boy, which provides AC power from a solar array. You can get a Windy Boy, which is provides wind turbine power onto the AC bus, and then drive your loads. Um, the battery bank, yeah, basically it's 48 volts nominal battery, and so you can use multiple different battery uh, chemistries on the DC side, anywhere from lead acid to uh, um, SLA or VLRA or a lithium ion or lithium iron phosphate. So, yeah. Any questions on that page? All right, next slide. Let's see. So this is my take on the um, way that it actually works, the inverter, the Sunny Island inverter. So let's start on the left. You have a 48 volt DC bus, and that you connect that to the inverter, and without any grid connection, you can start up the inverter and drive a protected load. Basically, I have a 200 amp or 100 amp panel that I drive with the inverter that supplies all of the house loads. So my house is being powered all the time by a 48 volt battery that goes through the inverter, and the inverter generates 60 hertz to run all the loads. Then there's a separate bus. If you look at the A2 grid slash generator bus, that has a bunch of it has anti-islanding detection on it, so it'll interrupt the switch that connects it to the grid whenever. And then you also have programmable control of how much current you draw from the grid. So if I say, for example, I only want to draw 10 amps from the grid, most of the power of the house will be coming from the batteries, and that will drive the load. Then the other real important thing is having the inverter generate a 60 hertz that's in phase with the grid. So whenever the grid is available or up, the inverter is basically providing a synchronous 60 hertz signal for the protected load, so that when you connect when the inverter decides it needs to connect to the grid, all of the 60 hertzes are in sync. In other words, you don't have a peak when the other one has a trough, and that would look like basically a dead short. Um, but anyway, that's kind of how that works. Any questions on that? Okay, next slide. Frequency shift power control. That's a technique where the Sunny Island inverter can actually vary the power of its output bus. Or, I mean, sorry, vary the frequency of its output bus by up to 2 hertz. And so, if you look at the chart, the if it's if the inverter is driving output power at 61 hertz, then you start to limit, you start to tell anything else that's connected to that bus to reduce their power. And by the time you get to 62 hertz, basically that would tell your solar inverter to stop adding current because I can't handle it. And so that's basically how the Sunny Island throttles the Sunny Boy to keep all of the power levels in sync, and so you don't overpower or overcharge the batteries. Any questions on that one? All right, next slide. So this is the main spec sheet for the Sunny Island 6048. Each inverter that in my system will only drives one leg of a split phase system. So each inverter is 120 volts. It's adjustable in frequency from 55 to 65 hertz, and it'll provide, almost 5,800 watts of continuous power at 77 F. But look at the surge current. So, for example, for 1 minute you can draw 8,400 watts. For 3 seconds you can get 11 kW without the thing failing. And then, of course, at higher temperatures, you start to having to reduce the capability. The nominal AC current for that unit is 48 amps. And the way I'm running my systems, I've got two inverters in parallel on each phase, so I can basically handle 96 amps from each phase. Um, and so also there's a maximum peak current for 60 milliseconds, basically about few cycles of 180 amps for each inverter. So the surge capability is quite good. The total harmonic factor on the output voltage is pretty good. It's not exactly a perfect sine wave, but it's filtered pretty well. Next slide. Of course, it can vary its output voltage from 80 to 150 volts. Let's see, maximum output current is 56 amps. Maximum input power 6.7 kW. Battery voltage 41 to 63 volts. And you can charge 140 amps into the battery at 50 volts DC. So two inverters in parallel would be able to handle 280 amps of charging onto the DC bus. It'll handle a bunch of different battery chemistries, some of them which need a battery management system to be safe. And it can handle systems up to 10,000 amp hours, which is a lot. If you take 10,000 amp hours times 50 volts, that's a lot of amp hour, a lot of kilowatt hours. Yeah. So next slide. The system Sunny Islands that I used are designed to be operated in parallel. So I have a one master, and then there's three slaves. So there's two inverters on L1 and two inverters on L2, and then the battery bus is common on all of the inverters. And that should be able to handle up a 24 kilowatt load on the system. So it's a pretty robust system. And next slide. Now, I like power stuff. In the Sunny Islands have the capability to do three phase. So if you ever have a project that needs three phase, one way to do it, and it may not even be the cheapest way, but one way to do it is to gang these Sunny Islands and run one Sunny Island per phase of the three phase, and you can initialize them so that you can generate pretty nice three-phase power that way. And that'll handle up to 18 kilowatts on three-phase. So if anybody has three-phase shop equipment or whatever, that's one way to do it. Next slide. This slide basically shows much more detail of the system that you could put together to run three phase. And of course, if you could run it in the four phase, the split phase as well with 4 units. But the Sunny Island can manage a generator. You can manage it with a automatic startup or with manual startup of the generator. And then it also handles the Sunny Boys that you see in red and blue in the upper quadrant there, and it will throttle those as needed using the frequency shift power control. Um, Next slide. All right, so that's sort of the end of the overview of the inverters and SMA Academy. Any questions? Okay, and I just put in a few useful, next slide. So this is the main menu for the master Sunny Island. There's a bunch of different meters that you can look at. If I'm looking at basically the right side here, section 200 are the settings. So there's inverter settings, battery settings, external settings for how you manage the grid, the relay settings. Each inverter has two relays that you can set up to trigger on various events. There's diagnostics, and there's failure reporting, and MMC, SD card logging, and so on. So it's a pretty robust, well thought out system. Next slide. So the main thing that I use is the time of day state of charge management. So the Sunny Island inverter has a very handy feature where you basically you can tell it from and what I do is I tell it that between 8 p.m. and 5 a.m. Keep the battery charged to 100%. Or actually, it only goes to 95% in that mode. So I keep the battery at night charged between 90 and 95%. The system will charge. Say the batteries get down to 10% charge by 8 p.m. at night. Then they'll charge at I typically charge at 50 or 55 amps off of the grid from 8 p.m. And by 2 or 3 a.m. They are fully charged, and then it stops charging, and then the basically the inverter keeps it charged between 90 and 95%. And then when it hits 5 a.m., then I use battery exclusively and until it gets down to 10%. And then I charge the battery up, even though it's not during the free period. I charge it up from 10% to like 20% and then go off grid and keep charging it. So next slide. I think I've got a graphic. Yeah. So this kind of shows graphically what's going on. So basically at night, there's a no cost to charge the batteries. But during the day, it's expensive. It's 26 cents rather than, 10 to 14 cents if you use power during the day. The purple line shows basically my battery state of charge throughout the day. So it starts at a low state at 8 p.m. By 2 a.m. or whatever, it's up to the peak that I want to charge it. And then it falls during the day. And if it falls below 10%, then I buy some power from the grid and charge the batteries up a little bit to keep it going until I hit 8 p.m. Any questions on that one?
Well, why are you charging before you get free power? It seems like you just switch your load to the grid and then start charging when the power gets free.
Well, the way I've got the system set up is all of my breakers, I inserted a second breaker panel. So all of my house is on the inverter breaker panel.
So nothing ever goes directly to the grid. So you're
Nothing
all
ever, correct. Yeah. And so actually what I'm doing is so normally I would charge at like 55 amps from the grid. But for example, if I see that by 6 p.m. I'm going to be down to about 15% or lower, what I'll do is then I'll set the inverters so that I only pull like 5 or 10 amps from the grid and basically keep the batteries at roughly the 10 to 15% range until 8 p.m. And then I increase the charge rate after 8 p.m.
So you're not actually charging the battery, you're just keeping it at the
Cor-
status quo until,
correct. Yeah, correct. I do that manually. And yeah, so that's the way that works.
so it's just kind of buffering through the battery.
Right, yeah. And basically the house runs off battery the entire time. It's never on the grid. Since it's a hybrid inverter, the inverter goes out and decides which it decides which well yeah, it decides which source is going to use to supply the current. If you refer back to that block diagram that I put together, basically there's a summer that sums the current from the battery over to the protected load. And so that yeah, so I'm basically the house is on battery all the time, and depending on how much I allow, how much current I'm allowing from the grid, it's either augmenting the current for the house, or it's actually if there's excess, then the inverter switches and uses it to charge the battery up.
Okay. Now, you have no solar, or do have you added some solar in now?
I do not have solar. I have a capability to add solar, but I figured it cost me about 10 grand to put the solar in, and
Mhm.
so why do it? I basically have battery storage, and in fact, TXU advertises that during the day when you're paying them 26 cents a kilowatt hour, that power comes from solar. So I'm doing my share to save the environment without having to make the capital investment of solar panels on my house and worry about hail damage and all that other stuff. Um,
So this is basically just a sizing issue too, where if you built your added more capacity to your system, you would never have to pay for the power, right? And then it becomes an economic decision of is it better to pay a little bit for power and keep your
yes,
sizing just below the threshold?
yeah,
Because some days on fair weather, you probably don't ever get to the
that's
point of having
correct.
to pay.
Yeah, that's correct. Okay, so next slide, and it shows a little more about that subject. Next slide, Jim. Oh yeah, here we go. So this shows my my electric bills actually from 2022 through present. And you can see the blue line, I was using a lot of electricity. And this was when I was on a fixed rate, and I actually I think I had a pool pump that I didn't notice was running all the time, and it cost me quite a bit of money. But once I got figured that out, let's see, the next line is the red. Let's see, 2023. Yeah, the no, the magenta one. Yeah. So my bill was running, on the order of 350 to 400 a month during the hottest part of the summer from, say, July through September, maybe into October. Um, and then last year, 2024, these were my electric bills in red. And you can see when I started in May, the June bill dropped to, I think, $130. And then July, I was out of town and I had the neighbor switch the house over to grid only. And that cost me some money. But then August and September continued to decrease. Now the green line is I've kind of figured out how to run the system, and my bills basically from November until May were on the order of $15 a month. Last month, June, I think my bill ends June 20th. The I think the bill was 30. I told my wife, "Gee, our electric bills doubled." uh, but they went to $30. So um, anyway, next slide. So this is a plot of my daily use, all the way from when I started the TXU free plan to roughly present. And you can see that last year, in the magenta, I was having to purchase a fair amount of electricity, even though there was a fair amount of free use. It did help. But then finally, by September, I kind of figured out how to do things. And then actually by February, I added another 15 kilowatt hours to the system. And did not have to use any purchased electricity until it started getting hot late May. And even so, I'm not using that much. I think the highest I've used is about 12 or 13 kilowatt hours in a day that I had to purchase. So it's pretty effective system. Any questions on that? All right, next slide. The other useful function that Sunny Islands have is they call it grid power enable. What that does is that setting will automatically connect the grid when the inverter load exceeds a set point. So I have mine set so that if the inverter is supplying more than 10 kilowatt for the load, it adds in the grid. And then it'll stay connected to the grid and purchase electricity until the load drops below. I think I've got it set at 8 kilowatts. So that's sort of a buffer. What that does is that, for example, if you think about how much current you're drawing out of the batteries, when you're doing 10 kW at 50 volts, that's 200 amps out of the DC bus continuously. And so if the house is drawing 10 kW, say you're cooking and using the dryer, and you don't have the grid backed up, and the air conditioner tries to start, then you'll exceed that peak demand off of your battery system, and the inverter will shut down to protect the batteries. So I use the grid power enable function to back up the system during high demand periods. Next slide. And I've threw in some useful links here on batteries. Okay, next slide. Next slide. This I showed last December, but this is roughly a diagram showing two of the four inverters, and the fact that neutrals are always connected to the Encore grid for this system. So it's not a separately derived system, and so it's got a single point ground for both Encore and this system. Next slide. Okay, so we made it through the inverter section. Now we'll move into LFP batteries, unless there's more questions in the previous section.
I have one question. What
Yeah,
if you
Bob.
wanted to just sort of like have that grid available when you needed those surges, like when the air conditioner compressors are starting?
Yeah. That doesn't work quite as well, because I think I haven't actually timed it, but I think it takes a little bit of time to do that. And I think my compressors they draw current for maybe 10 cycles, so maybe like 150 milliseconds. They'll draw a pretty high current. And by that time, I think, yeah, the batteries might complain. So, um,
Okay,
yeah.
so it would take some effort to get that coordinated so that like your air conditioner could tell your inverter that it was going to start, so it would get ready for it. And
Yeah,
there is a way
well,
to do that, by the way, I know about.
okay, all right. Yeah.
But
Yeah.
okay.
So my solution, I had my initial solution was to add the super caps. I've got 260 farads on the DC bus, and that tended to stop most of the inverter faults that I was seeing with overcurrent. Uh, but then I also added that another 15 kilowatt hours of battery, which we'll see in a minute, onto the bus, and that also helps the drop the surge current for each individual pack. And so that was a big help too. So uh, my solution last summer to not have the house go down when the air conditioner started was to from about 3 p.m. on, I would tell the inverters to draw 7 amps from the grid, and so that isolation switch was always connected to the load part. And so when there was a huge spike, when the compressor wanted to start up, that would actually be supplied by the grid. And of course, that's not very many kilowatt hours, but it is a little bit. So that actually provided my stability solution for the system.
So the charger kicks in when you're at its maximum rate when you detect the load.
Um, well, okay, so the Sunny Island actually supplies the load 100% of the time from battery. But the grid is in parallel with the protected load whenever it's connected. And I can tell the inverter how much power, how much current to draw from the grid. So when yeah, it's a little bit of a manual operation to keep the current the grid current settings to the level. But on in the default, basically I draw about 50 amps from the grid when I want to charge, and and so that will charge up the batteries. Um, Whenever it hits 10%, it'll charge at 50 amps until the percentage of charge gets to 15%, and then it drops off the grid. So there's a little bit of manual operation that I'm having to do to manage uh, things, but um, in general, it works pretty automatically.
So is your deficit before you put it even added the supercapacitors on here, you had a deficit where you couldn't draw enough current from the battery packs without them overloading, um, and that's without any grid power being applied, right?
That's correct. Yeah.
So
But, and
could
when
you have set it up so that you had made up that deficit from the grid uh, instead of using the capacitors or extra load?
Yeah, right. I could have. I didn't think of that at the time. It's been quite an education, to tell you. But yeah, I could have set that up. So probably eventually I'll take out those super caps. I think they help somewhat. They definitely help somewhat. But as I'm actually currently have batteries on hand for see 675 about 75 to 78 kilowatt hours, and that
That's a lot.
yeah, that's quite a bit. And we'll see it later, but I'm still building that last battery pack. But
Mhm.
yeah, so yeah.
So the
uh,
super caps are really probably not a consideration at this point.
That's right. Well, I mean, they do help a little bit, but it probably was the wrong direction for me to go. I probably should have added more battery capacity right away than adding super caps. But I was desperate for a solution, and
Yeah, I
I
think you were
found
saying
one.
there was a time aspect to it, and there was more delay for getting batteries than the getting the caps.
That's correct. Yeah, that's correct. Yeah. Yeah.
But
So, okay.
I guess the downside of using the grid to apply that extra power is that it would be great as long as the grid's up, but if you have the grid goes down, then it does no help at all. And
That's right. That's right. That's right. But I think, yes. Yeah. So I had one situation recently, I think last week, where the grid went down for the neighborhood right at about 8:20 p.m. My batteries, I I plot the charge of the batteries so that by 8 p.m. they're down to about 10%. Well, the when the grid went out, I wasn't able to charge my battery, so I couldn't run the house. And I started up my generator, but I don't know, there was some kind of issue going on with the generator, and I could only charge 2 kilowatts off the generator, which was not enough to cause everything to shut down. So basically, a week ago or whatever that was, I had to shut the house down because the grid was down, and it was only down from 8:20 until 11 p.m. So 2.5 hours or so.
Mhm.
But I was chagrined to have been caught with that situation. So basically, my notes are don't let it go down below 15% anymore,
Mhm.
10%, because if you have a grid power failure, then what do you do? So
I can see that you probably have a side benefit of having a lot better power quality than anybody else in your neighborhood because you are isolated with any transients on the grid.
that's correct. Yeah. In fact, it's very interesting. I do have I have a let's say what do they call it? A home assistant, HA. I don't know if you've run across those, but I monitor the power I draw from the grid. I monitor the AC, both AC units, how much power they're drawing. The interesting thing is during the day when I'm running off the inverter, my voltage is 240 volts, and it does not vary. Oh, yeah, when the far air conditioner kicks on, maybe I can see a half a volt dip in the grid, but that's just wiring issue, or I mean, grid
Mhm.
wire resistance. But I monitor during the day the grid voltage, and the grid voltage varies all the way up to 252 volts to 253. That the high end of their spec, all the way down to 238. And so the power company is, having to play with their grid voltage in order to keep the demand properly. So I can see when the neighborhood, when the weather is hot, the voltages tend to be low. And if you look at ERCOT, then sometimes you'll notice that the grid frequency is slightly below 60 hertz, and they're maybe 2 seconds behind because of the demand. But so yeah, I'm running 240 volts, 60 hertz pretty much all the time.
And you're completely isolated from any like lightning strikes on the line or whatever.
That's correct. That's correct. Yeah. Yeah. Okay. So here's the specs of the units that I bought initially from China way back almost 2 years ago. They are 228 amp hour cells. They each store 11.6 kilowatt hours of energy. And they're 24 by 12 by 22 size. I have four of them, and they each weigh about 205 pounds. They say that the max charging current is 100 amps for each unit. You can discharge at 100 amps. Peak discharge is 200 amps, but that's only a few microseconds. And the battery management system allows it to coordinate up to 116 kilowatt hours of storage.
Now you say peak 200, but didn't you say earlier that it was actually limited to 110?
Yeah, I'll show you that page in just a bit. And see, also the battery works on they're as basically the CAN bus is what's used to control the inverter, and then to control the battery packs themselves, it uses a funky protocol on RS-485. And anyway, the next slide. So they'll work from 4 below Fahrenheit to 150 Fahrenheit, non-condensing, relative humidity, altitude up to pretty high, 10,000 feet. They did pass European standards for uh, battery storage units, so the TUV standards. And the protocols that the batteries will support are they'll support SMA, Dye, Growatt, Schneider, Outback, or Victron, and others. The design lifetime of each pack is about 30 years, and they'll cycle 8,000 times all the way down to 100% depth of discharge, and it'll still last for 30 years. Um, let's see, yeah, so it's pretty amazing technology. You take a lead acid and deep cycle it, it'll probably last 2 cycles. Next slide. So here's some pictures inside those batteries. You can see there's 16 cells. They're in series, and the battery management system is sort of on top there. What they all do is they interrupt the negative lead for safety. And there's voltage sensors on each cell, as well as I think there's 3 or 4 temp sensors. Next page.
Why the negative lead, not the positive lead?
I don't know. Probably yeah, but I don't know.
Well, in telecom, they when they run battery systems like this, they run a positive ground. So maybe it's a throwback to that.
Yeah, I don't know. Maybe. And so when you hook them all together, actually I found out later that the BMS that they're using in the RJ lithium battery packs is PACE, and that PACE is a Chinese manufacturer that has been building BMSs for quite a while, and they basically are an OEM supplier of that, but it's a pretty good battery management system with a lot of capabilities. So I've got the 4 battery packs connected by RS-485. Each battery pack gets its own address, and so address 1 is the master, and then that master communicates via CAN bus to the inverter. Um, anyway, next slide. So here was the default battery management settings. That's factory default. And you can see in the lower left in the red, I've got circled, it hit protected mode at 110 amps for 1 second. And it actually would protect also if it had a short circuit of 150 amps for only 100. I think I can't read that. Is that a millisecond or microsecond? I think that might be microseconds. I can't tell. But anyway, so that default settings weren't particularly didn't quite match what they were saying on their advertising site. Um, so um, there's a whole lot of information in this slide on how to manage batteries and so on. The battery management system tries to keep track of the state of charge of the battery, and that's a difficult task. But what it does is when the battery pack gets up to a certain voltage, and the current falls to a certain level, it'll reset the state of charge that it's estimating to 100%. And I had to play with those settings in order to get it to work properly. Next slide. My current settings, I changed things a little bit, and so I now have the protection of set at 150 amps for 5 seconds or 5,000 milliseconds, and it protects at 200 amps after 100. I think that's 100 microseconds. I can't quite read it, but yeah. And then I set the state of charge reset to 55 volts. If you take 55 and divide that by 16, that's a voltage per cell, essentially, that it resets the state of charge calculation to 100%. Next slide. On each of the packs, you get a readout of what each of the 16 cell voltage is. So in this particular screenshot, the voltage of the pack was, actually the whole DC bus was 54.476 volts. That particular pack was drawing 7 amps. It was at 91% state of charge. And now the cell voltage there was 69 millivolts difference between cell 15 and cell 7. So I had one of the series cells at 33.434 volts, and the lowest one was at 3.365 volts. So that's so basically with the monitoring system, you can tell what each of your cells are doing, and it's real important to keep all the series cells uh, roughly the same state of charge. Now you have them all in series, so there's not much you can do for each individual cell, but the battery management system has capabilities, and we'll get into that later, on how to control the charge levels on each individual cell. Next slide. This showed trouble that I was having last year with battery state of charge balancing. And I think I got somewhere around 20 to 30% difference between battery packs 1 through 4 of the RJ. And what that so then the inverter is trying to control how much charge you've got based on state of charge. And what was happening is that the master battery pack was, when you were charging the battery packs, it would report the highest state of charge, so you wouldn't overcharge it. And then when you were discharging the battery packs, it would report the lowest pack state of charge. And so I had about a 30% difference between and that would lead to funky behavior on the inverter. And I couldn't, basically that 30% difference, I was losing that capacity. And so I had to figure out how to keep the cells and the packs all balanced to roughly the same. And anyway, and I did do that. So next slide. This is a little aside of how I got up to speed on what was happening with between the battery packs, battery management system, and the inverter. So Adafruit has a really slick CAN bus, dual CAN bus feather, they call it. And I 3D printed a housing for it and added a second physical invert layer for the 2 CAN buses. So I basically logged the CAN to BMS communication to see I could see what was going on, and had plans to modify the CAN traffic between the BMS and the inverter so that I could basically get rid of or overcome this state of charge difference. Yeah, anyway, next slide. So the routines that they provide with the feather can, they've got a interrupt driven driver, so that whenever a certain pa packet address occurs on the bus, it'll give the CPU an interrupt, which is really efficient. So this is just a snippet of code that shows when the CAN bus packet 305 arrives, and here's what you do. And so basically, I convert, I convert I think packet 305, we'll get into later, but has a number of different parameters. But so this decodes those parameters and prints it out to the serial bus is what I was doing. Next slide. Then this was a different set. So when packet 351 arrived, these are the things that I would do. And this is a C++ code on the Arduino IDE. Anyway, next slide. So here is kind of the heart of the protocol between the inverter and the battery management system. So what happens is the battery management system sends different packets. So there's packet 351, 355, 356, 35A, 35B, 35E, 35F. And about a 1 hertz rate, the battery management system sends those packets with the data to the inverter. And then about once a second, also, the inverter sends back packets 305 and 306, indicating, okay, here's what I have for battery voltage and current and battery temperature and state of charge, and also state of health of the battery and what's going on, a few other things. The key thing is packet. Well, let's see. The main control thing is packet 351 from the battery management system. And so what that packet does, it tells the inverter, set the battery charge voltage to, and I have mine set at, I think 50, I can't remember, 52.3, either 52 or 54. And then how much maximum charge current it'll handle, how much discharged current it'll handle, and what the lowest discharge voltage can be. And that is real key. And packet 355 sends the state of charge of the battery up to the inverter so that it can change state and keep things in line. So, and then packet 35A has all the alarms. So there's warnings, which the inverter does nothing with, and then the alarms, which will actually shut down the inverter when things happen. So if the BMS detects that one of the cells is over voltage, it sends a packet out on 35A, and the inverter will see that and basically shut down. So that's basically a closed loop control system between the battery management system and the inverter. Any questions on that page? Okay. Next slide. We'll go into building my new LFP battery pack. So if you're going to build your own battery, there's, basically construction requirements, safety requirements. I'll show you the LFP equivalent circuit and some voltage and current state of charge curves, and what the BMS equivalent circuit looks like in some case assembly pictures. Next slide. So on this timeline, in October of last year, I ordered 16 LFP cells from Battery Finds. They were 340 amp hours. They weren't cheap, but I ordered them. And then November, hadn't heard anything from Battery Finds, so I ordered 16 280 amp hour cells from Ducan, which is a really good outfit. And in 2 days, I got 16 280 amp hour LFP Eve cells. Eve is there's a number of manufacturers of lithium iron phosphate cells in China. Eve, Goshen, Cattle, which Ford is working with, building their battery plant in Michigan using Cattle, CATL technology. So there's and then there's probably a few others. Um, I was pleasantly surprised by the end of December, I got 16 340 amp hour Goshen cells. And January, I ordered a case for those. I originally was going to build my own case, but then I found that you could buy a case on Alibaba. I think I spent 550 or maybe $600 for a case with the battery management system built by JK. And so and then I ordered also a CAN bus control system from James. I said it's James Technology, but it's James Tronics. And he's an Australian guy that's really figured out how to do the CAN bus control on heterogeneous systems. And I'll show you some more details on that later. And then by the Valentine's Day, I had my first homebrew case assembled, and I brought it online. So then I had 60 kilowatt total, so by February 17th. On March 30th, I said, "Oh, that worked pretty good. Let me order another case." And I ordered it, but by April 8th, they came back and said, we can't ship due to 150% tariffs. So that order got canceled. And then things straightened out a little bit by May 13th. I ordered a case on May 13th without the BMS, and it finally arrived June 20th. And I'm still planning the modifications that I have to make for that. It's still in progress. Any questions on this one? Next slide. Okay, so these LFP cells are rectangular. The traditional cells have been cylindrical, but the industry, particularly I guess the car industry or whatever, and a lot of manufacturers have switched to this rectangular format for easier packaging. It is about 3.2 volts nominal voltage, and you can get them anywhere from 50 to 350 amp hours per cell. Now, interestingly, they define a C rate as how many amp hours is the rated amp hours for 1 hour. So, for example, if I have a 100 amp hour battery, a 1C charge or discharge rate is defined as 100 amps. And of course, if I have 16 cells in series, that'll give you about 51.2 volts nominal. And you absolutely have to have a battery management system in there for safety. Their aluminum cases they also only have a thin poly film on them, so you need to isolate. The case is connected to either the positive or the negative, one of the terminals, so you have to isolate those. The picture on the bottom is basically how they're rolled. So basically, it's just a big, it's kind of like a capacitor, probably, all wound together with stuff in between. So, any questions on that one? Next slide. So when I got the Eve cells, they sent along a spec sheet, and they talked about cell compression requirements, and I wasn't aware of that until I got the cells. But what this shows, if the top left cell, is that they're testing with cycles of on the system of how long the cell would last until it hit 80% state of health. In other words, it would hold 80% of the original capacity. And that was only, it looks like, let's see, I don't know how many cycles. I can't quite read that. 800 cycles. But if you compress the cells and keep them from expanding, or actually put about 2 psi on them, 12 psi on the y-axis on the skinny side, that you would lengthen the cycle life by a significant amount. So so basically, um, I decided I had to figure out how to keep the cells in compression in order to maximize the life on them. Any questions on this page? All right. And then this is a slide from some of the battery uh, modules and how they do things. They basically provide a sandwich, and they have a compressive plate that they use to pull the cells together. And they actually have cooling on car batteries to keep the batteries cool. Um, some of the batteries use there's a Rogers makes a pour-on basically it's foam. It looks like foam, and it has about 12 psi of compression that helps keep a constant compression on the cells. Anyway, next page. So on the forums, there's a ton of different homebrew compression schemes. I've grabbed pictures of several of them from the web, and basically some guys use springs actually to compress it so that you get a variable, so that basically you don't exceed the pressure on the cells when they charge and discharge. There's a bunch of different schemes. And anyway, so there's actually a trend away from springs to using compression foam. So anyway, next slide. So now here is a equivalent circuit of one cell. And so basically what you have on the left side, you have a variable voltage, depending on what the state of charge is, anywhere from 2.5 to 3.65 volts. And in series with a pretty small resistance of about 1.5 milliohms. But the big thing is the cells basically look like big capacitors, anywhere from 100 to 500 K farads. So that's 1,000 farads equivalent in parallel with a small resistor. And that produces the output voltage of the cell. So what happens is the voltage of the cell depends on how recent the charge or discharge event was. And if you calculate the RC time constant, it's about 5 minutes. If you take 1.5 milliohms with 200,000 farads, it takes 5 minutes just for the 37%/63% point on the cell. So anyway, yeah, so capacitance has a huge effect, and that's the reason that you can't directly measure the cell state of charge by measuring the voltage of the cell. Next slide.
Well, before you go,
Yeah.
I think you have an error on this. The RP, I think you copied the RI value. I think it should be much higher value on the RP. It says 1.5 milliohms for the RP, but I think that's the value for the series resistance, not the parallel resistance.
Well, I actually think it's both. I think the effective parallel resistance across the equivalent capacitor is also about the same as the Ri.
Well, it would just short out the capacitor if you did that. I mean,
well, yeah, it does. Right, it does.
I mean,
That's what
it would instantly discharge it. I mean,
Well, not instantly because it's 500,000 farads. And that's why the RC time constant is 300 seconds or 5 minutes. Uh, if you go to the next slide, I think that might
Okay.
clarify some
Sorry,
things.
sorry for
Yeah. Yeah, no problem. Good question. So this charge shows the effect of that capacitor. And the solid lines are the charge voltage. They're the voltage at different charge levels, and the dotted lines are the voltage at different discharge levels. So if you're, for example, charging at a 0.2 C, so 0.2 C would be it'd be roughly if you're charging at roughly 20 amps, um, then your voltage will be higher because you're charging up that capacitor that is in there. If you're only charging at a low rate, 0.1 C, your cell voltage at the output is maybe I don't know 50 millivolts lower. And then similarly on the discharge size, you get the same kind of a curve. So the blank spot in the middle of these curves is probably the cell voltage when it was rested after the equivalent capacitance is all discharged and equalized. Um, so it so that effective series capacitance makes it basically so you have to count coulombs going in as opposed to looking at the voltage of the cell in order to get a proper state of charge. Any questions or observations on that?
I have a question on the pressure. What is the pressure actually doing to the battery?
Well, what it does is it prevents the sides from bulging out. And so can't remember if maybe I have something later that describes that. But um, if you don't, when you charge the electrolyte tends to want to swell, and when you discharge it, it'll shrink. So basically, the battery is breathing on and charge and discharge cycles. And that breathing, depending on how the cell is constrained, could put stress on the terminals that you've got tied together, at the top.
So you're compensating for a poor case design.
That's correct. Yeah, yeah, that's right. And the manufacturers say, hey, put about anywhere, I don't know, whatever the spec is, from 5 psi to 15 psi is about good. Because right. And of course, the traditional cylindrical cells um, don't have that issue because well, I don't know. I think they're better constrained. Cylindrical cells are better constrained. They don't breathe. Yeah, that's my understanding. Okay, next slide. All right, so what I did with this picture is to try to show the what the battery management system actually does connected to the hybrid inverter. So the inverter is either acts as a voltage charging source or as a load, depending on which direction current's flowing for the battery. So for example, when the hybrid inverter decides to start to charge, yeah, basically both of the MOSFETs are on, and default, if you look at the FETs at the bottom, the default is they're both charge and discharge is on. But if the control system decides that, hey, I'm overcharged or whatever, it will shut off the charge MOS, and the substrate diode will prevent current from flowing in the charge direction. Similarly, if you're discharging and the BMS decides, hey, too much current, it will turn off the discharge FET, and that will use the substrate diode as the blocking diode to prevent the current from flowing from the battery. So that's basically how protection mode works for the BMS. Now, cell balancing, along the right side of the diagram, you see voltage of cells 1 through 1, 2, and up to 16. And those will vary from 2.5 to 3.65 volts per cell. But keep in mind, the inverter can only charge the whole set of 16 in series. So what happens is one way to do it with passive control is there's on that sense wire for each cell, there's a 470 ohm resistor that will either be cut in or out of and parallel to the cell, so it will leak a little bit of current from that cell and cause the other ones to get charged more. And so that's the technique that the battery management system uses to try to balance the cells in parallel. So any questions on that? Okay, next slide. And here's a couple different versions of BMS boards. So the top one is a TDT. You can see that the MOSFETs are all heat sinked. And on the bottom left is a whole integrated module from JK BMS. And then here's a discrete JK BMS BMS board. Next slide. And they also sometimes you can order them different ways, but a lot of times they'll come with a BMS LCD screen and also the communication board that plugs into the BMS to provide RJ45 for CAN, RS485 or RS232, plus LEDs for charge indication and address switches for address setting. Next slide. So what I've done is, due to the fact that I have a PACE BMS for 4 of the batteries, and then I've got JK BMSs for another 2, basically they all have to talk together and to be able to successfully manage the system with the inverter. And that's done the way I found a very good solution using James Tronic's little ESP8266 boards that do this. And so there's I had to buy I think 3 different boards that that basically the master IBMS looks at the stuff coming from the the slave IBMSs and sends the correct response to the inverter so that it can charge the bus correctly. Anyway, any questions on that? Okay, next. And this is one of them. There's basically a CAN bus interface and a RS485 interfaces and interfaces for various different types of inverters or battery packs that it's controlling. Next slide. So here are pictures of the case that I bought from China. I believe that these cases cost around $300 now. They're probably $100 more expensive than they were 6 months or a year ago. But they're 16 gauge steel. They're probably built in an automated factory and automated welded, or I think they're robotically welded. You can see the little welds for various things. and they're weight optimized. So I think the only weigh maybe 20 or 30 pounds just for the case, but it's 16 gauge steel is pretty robust. Next slide. So you have to isolate the cells, and so they come with some I don't know, FR4 circuit fiberglass boards that you put in between each cell to isolate the cases from each other and from the case. Next slide. This is actually a pressure plate that goes in the end, and you screw it down, and that provides a pretty good compressive force against the cells. So there's 8 cells, well, yeah, it's 8 cells to the end. There's 2 rows. So and then on the top there is a brace as well that ties things in. And they have standoffs for your battery management system board already either TIG or MIG welded to that pressure plate. Next slide. They have a nice front panel to fit all the electronics. They've got battery minus and battery plus, and spots for all of the Canon RS-485 stuff, and a hole for the circuit breaker and power on off button and so on. The backside is on the right, and they have standoffs on that so that you can mount things quite easily. Next slide. This is a picture of how the electronics goes together. Basically, there's a bus bar so you've got basically 2 terminals for positive and 2 terminals for negative, and those terminals are in parallel. BMS mounts to the pressure plate, which goes in the back, and then other circuit boards are there. Next slide. So put all together, it kind of looks like this. This you can see there's on the picture on the left, there's the red wiring that goes down to each cell. Those are individual wires that go and terminate out the BMS board. That's for measuring the voltage of each cell and for intervening a little bit on how much current. The board that the case that I bought actually has a circuit board that with a wiring that connects into the battery management system, but it makes it a little more easier than having to hand wire all 16 cells. Next slide. I recently found this battery trolley. Basically, it's a heavy-duty platform on rollers that locks into that you can put the case on, and locks and makes it mobile. So you can put 4 battery packs stacked on top of each other, so it will handle about 800 pounds. Next slide. Here are the Goshen 340 amp hour case cells that I had to modify. Those cells are about 10 millimeters thicker than the standard Eve cells that the do-it-yourself case is made from. So I chopped off the front end of the case to preserve the mounting for the front panel, and then I'm using pour-on spacers on the cells. But in order to do that, I have to add 4 inches to the length of the case. So I've got some 16 gauge steel and so on that I'm going to and some other rectangular steel that I'm going to use to extend this by about 4 inches so that I can add the pressure plate onto the cells. And I'm planning on TIG welding that 16 gauge steel altogether. And I should have that online by this fall, which I don't really need, but by next summer, it'll come in handy. Any questions on this one? Okay, next page. Links, next page. Okay, so I thought we would put together, well, if you wanted to make a field day portable power source, you could use a Sunny Island, a do-it-yourself case, and a little bit of breaker box, and you could put together a 120 volt system, handle 5 kW, have 15 kilowatt hours of a capacity. You could charge it back up from any 120 volt outlet, and you could probably do it in about 10 to 13 cubic feet. Of course, it's going to weigh about 400 pounds because these things are heavy. Next page. The other option is to do they call them solar trailers. And you can buy a trailer with two Sunny Islands and some electronics and actually solar cells. And if you did that, you could have 240 volts, 15 kilowatt hours. Of course, you'd have a trailer and that'd be 1,500 to 2,000 pounds, whatever. But those are another options that, and this would, if you had the solar cells on the trailer, that would let you basically run permanently off grid and have roughly, 5 or 6 kW at 240 volts available. So you could run your AC as well. Next slide. All right, this whole last section is about energy storage system standards. Next slide. There's, of course, we've already alluded to 1741 for anti-islanding. NEC Article 706 talks about energy storage systems. Not UL 9540 is the UL code for that, and 9540A is basically it is the NFPA test procedures for a battery system. And then Article 710 is for standalone systems, 690 is for PV standards. And it's important to understand all of those if you're building a system. The only thing I'll add on here is that Article 706 was added in 2017. So when I got trained on inverters and all that kind of stuff, we didn't have to worry about battery storage systems, but NEC and I guess National Fire Protection has decided that you need to add some additional capacity tests for battery storage systems. That's about it. Next slide. I don't know that we need to get into the details on these standards, but they're in the slide set. I think Jim will post those on the website. You can go next slide. Basically, there's any system that's intended to receive or store energy, including electrochemical, chemical, mechanical, and thermal, are now ruled by UL 9540. Next slide. And that thing there's construction requirements, short circuit requirements. They do large scale fire testing on these things, and then they do a safety analysis of the control system. So all of the CAN bus stuff talking with the inverter, they want to get their mitts into that and make sure that that's correct. Next slide. They do, of course, electrical performance and EMI testing. Next slide. They do structural rigidity, water, salt fog exposure, and then they test the manufacturers. They need them 100% dielectric breakdown tested, and whether or not the manufacturer has production quality controls to ensure that everything is kosher. Next slide. And then the testing stuff themselves, there's cell level tests, there's module level tests, unit level tests, and thermal and installation level tests. And these are all checking for thermal runaway and that kind of thing. So, basically they try to put the device in the worst case scenario and see how it works. Anyway, next slide. Yeah, and then NEC Article 690, we've covered a lot of this stuff. There's different types of systems in Article 690, and anyway, so this details what those are. Go ahead. So there's a interactive PV system, and of course you can see why you have to shut down solar because it's directly connected to the grid, and you have to protect the linemen. So unless you have a transfer switch, you've got to you got to shut down unless you have well, and due to if you only have solar. Next slide. I think and now there's a bunch of new stuff, and in fact, I saw a recent article from TI that says they're working on basically solar conversion directly from PV to AC, and those are systems that are going to be available. And yeah, anyway, but this covers that. Next slide. So there's DC coupled multi-mode systems, and then there's the next slide, AC coupled multi-mode systems, and that's the approach that I talked about in this presentation. So yeah. Next slide. And of course, if they're not grid connected, you still have to have some standards, but you don't have to worry about anti-islanding. Next slide. Okay, so that's a quick rundown of the standard section. Yeah, anyway, I think that might be about it.
I got a question for you. How much, if any, RF hash have you experienced with systems like this?
Not a lot. I haven't actually looked at that because I don't get on the air much, and but if you look at the output waveform in the scope, they've got a lot of filtering on the on the inverters, and so there's very little hash, if you will, on the power line.
Excellent.
Okay, I think that's it. Sorry it took so long.
Oh, don't apologize. We're really happy that you got to roll through all of this. Obviously, this is a passion, and each of us have something similar. There was a question or a statement put into the chat from David where he said he's been working on a 12-volt pack using some cells. He put in a link. You want to talk about that for a minute, David?
Oh yeah, happy to. So the cells he's using to build those big batteries, I just took 4 of them and made a 12-volt pack, right? It's
Yeah.
pretty heavy. My plan is to put an inverter in that and make it semi-portable because it's even 4 of those cells with an inverter, it gets a little hefty for one person. So I'm about halfway done building it. I used some parts from a website, Jag35. He made a PCB plate with bus bars that go on it and has all the connectors integrated, and you just kind of bolt it together. And I ordered the compression plates from him as well, and I put the dimensions of the compression plates in the Flickr gallery. If anybody wanted to roll their own or had a press break, you could easily make your own compression plates with just 4 cells if you wanted a 320 amp hour 12-volt battery. It'd run you a while on some of these outings, but
Yeah, I
my
think
plan.
just there's a lot of 12-volt systems and they work pretty well. If you have a 200 amp hour cells, 4 of them, and at 12 volts, that give you 3 to 4 kW depending on your cell.
Yeah.
kilowatt hours, actually 3.3 to 4 kilowatt hours of storage. And that might be enough to run, particularly if you're not running a lot of power out to the antenna.
Right. That was the design goal of the one I was putting together. So
Yeah,
it's about half built, and that building batteries is a lot of fun. So this was an interesting topic, Doug. Thank you.
absolutely.
Doug, that is a really great job of the presentation, and a lot of effort has gone into it, and we really appreciate your time. I was pulled in myself to a couple of parts of the presentation. One is the weirdness of parallel batteries that have their own BMS.
Oh yeah.
Yeah.
Yeah. Well, we're testing some beacon operations, and they include a solar controller trying to charge two batteries in parallel. And now I realize there's a lot more behind that. I just went out and pressed the button that told me how much voltage was on that. You've already taught us that that doesn't mean a lot. One of the batteries just charged directly in 8 or 10 hours. It had it was sized at 24 amp hour, and the beacon's pulling about 3 amps.
Yeah.
And then the other one just didn't even give any help at all.
Yeah. There's a whole, and I probably should have included it, but I do have some uh, do's and don'ts on how to connect batteries in parallel. And current sharing is real important. So the resistance, like say if you had four 12-volt batteries and you connect all of the negatives together and all of the positives together, and you connect a lead from the end one on negative and the end one on the positive all the way to your load, the other batteries are not going to be able to participate as much as the lead battery, right? So there's a whole art to doing the milliohm, resistance between all of the parallel batteries and where you should pull current out so that the current density is proper across all of the batteries. And it can get real complicated.
Do you have a presentation already on that?
I have, let me look. I don't have the presentation, but I have slides. Let's see somewhere if I can find them. Let me look.
Yeah, not for today, but
Yeah.
I think we could use that also in the work that we're doing.
If you'd like, yeah, sometime later I could put together a short presentation and that won't be this big, but yeah, I could cover that.
Great. Yeah, well, it would help me, I can tell you that. But yeah, well, it'd help our club because we have a strategy to put these beacons out there in a prototypical environment. So, in other words, we want to set them up temporarily. And I've got a solar panel, I've got a solar controller. We have the beacon, it's cranked up on a mast, 30 feet high, transmits on two different millimeter wave frequencies.
Yeah.
And I've noticed that my naive idea of how to parallel these batteries is not working.
Yeah. Yeah. Yeah, I could put that together. I don't know. Maybe I could do that for your next meeting in August, depending on when the dates are. But I should be able to cover that in half an hour or something like that.
Great. We have a meeting in August and also September every month. So
Yeah.
I'll
Yeah. Okay.
talk with you offline about that.
Yeah. Okay. Great.
I'd like to make a couple of comments if I could
Go
about
ahead,
this.
Bob.
I'm very interested too. I found it very interesting, Doug's presentation. I've got this backup generator here on my home, and I know Al has one, and other people have them. We got transfer switches and deal with some of these issues, but not a lot of them. But the concept of the peak loading is the most demanding thing, and it drives the whole system to a certain extent, it seems like, or the cost or how big a system you build.
Right.
It's really kind of sad because, well, new air conditioning systems are going to be designed with DC motors that have a variable startup current, so they don't have that real high current as
That's right.
in the future. So you're going to see that need go away. A lot of people have switched to LED lighting, which is bad for amateur radio because it's added the RF. But on the other hand, if houses were wired differently and you had different power sources, you could power all those LED lights directly. And there's a lot of loss, probably 30 or more percent loss in the converters that are being used in LED lights. So there's a huge possible impact on the future of homes and power but the public is so not aware. Amateur radio people tend to understand the technology a little bit better, but it just is a fascinating thing that you're showing here. And the concept of, we all use a lot of computers and little Raspberry Pis and other things in our amateur gear. And if power drops off of those things in a sudden way, you can end up losing the operation of that equipment. So if you have battery backed up systems that continue to function as your other power source is interrupted, which is usually for a brief time, it can save you a lot of heartache, I think. So there's
Yeah.
just a lot of lessons in this presentation and for amateur radio purposes also. Anyway, that's some of my thoughts.
Yep. Thank you.
Thank you again, Doug.
You bet.
We're going to move on to amateur radio on high altitude balloons. And there has been some activity recently. I won't try to explain it. We have the expert here. So, Andrew, are you ready?
Yes, but question for you and I guess the group. I mean, we're a couple minutes short of 3 o'clock, and I need at least an hour, maybe a little more to get this one done.
Sure.
Should we do it now or should we kick the can?
No, let's do it now. We won't even take a vote on that.
Okay. And do we need 5 minutes for everybody to go grab coffee or restroom break or anything, or should we just charge straight into it?
Yeah, I think people are probably taking that break that you're talking about. I did.
Okay.
And just go ahead and take control.
Well, let's do it.
I think
I
you
will.
stop sharing at the top of the screen, Doug, on your, or
Well,
no,
that would be Jim.
okay, Jim, I'm
Okay.
sorry.
All right.
All right. Can y'all see a map on my screen?
Yeah.
All right. So we're going to start off with what I call the Project Horus ecosystem. So, real quick before we get too far into this, I'd suggest you all click the view button up at the top and go with the speaker and screen side by side, because I do have some toys here on my desk, some props and stuff, trackers and other payloads that have flown, and I'll hold those up and show them. But anyway, the kind of basis for the software we fly on these weather balloons is the Project Horse ecosystem. And so we'll run through this real quick. I'm Andrew, KE5GDB. I was licensed in 2005 in Houston. I moved up here in 2012 to go to school at UT Dallas. And since then, and actually well before then, when I still lived in Houston, I participated with a number of high altitude balloon groups. There's the South Texas Balloon Launch Team. The Plano Amateur Radio Club had a very active group about 10 years ago called Park Balloon. These days, the Richardson Club is kind of taking the reins over for that, and we're calling ourselves the Richardson Area Balloonatics. There's been a couple other groups like the Stratocasters, the Arbonet, the amateur radio balloons over Northeast Texas, a couple different balloon groups. And I've also made an appearance at some high altitude ballooning conferences, and in particular the Great Plains Super Launch. That's somewhere in the plains every year. It rotates depending on who wants to host it. So the Project Horus group is a special interest group of the Amateur Radio Experimenters group. These are some really smart people out of Australia. And most of what we fly right now implements things that they've programmed. I've personally contributed a fair amount of code to this project just to add features and do little things I want it to do. But these guys are a really smart bunch, and we implement a lot of what they've written. So we can kind of divide it up into three categories. There's the payloads, the reception, and the display. And so from a payloads perspective, there are two technologies we'll talk about. There's Horus Binary, which is a low speed, low data rate tracking protocol. And then there's WeNet or WENET, depending on who you ask. And that's a higher speed protocol that's meant to move images in addition to GPS and other telemetry data. The images are stills in this protocol. From a reception perspective, there's three ways to receive Horus Binary. There's a web receiver, and I'll actually demonstrate that here in a minute. There's Horus GUI, and if you're running a Raspberry Pi with like an RTL SDR dongle, there's the Horus DMOD library. WeNet also just has a Docker image that receives it very well using like an RTL SDR on a Raspberry Pi. And then to display it, we use SonTub Amateur. SonTub Amateur is a website that can be accessed anywhere. Hang on, my cat is about to crawl across the desk and she's stirring things up here. SonTub Amateur is, the website, public access. Everybody can see that easily. ChaseMapper is very similar, but that's more for local access, and that runs locally on a Raspberry Pi that you might have in the vehicle while you're chasing these balloons. And then to receive the images or to view the images, you can view them on ssdv.habhub.org. And most of our recent flights have had a transmitter that does convey images to that website. And we use satellite stations or greater to receive those, just due to the SNR required to achieve that decent reception. That usually runs like 115.2 kilobaud, so you need a little more SNR than the Horus Binary protocol. So Horus Binary, what is this? This is actually a pretty neat protocol, and this is an APRS direct replacement. I do not fly APRS on my flights anymore. Horus Binary tends to work really well, and really quick, let me change a zoom setting here so y'all might be able to see the animation a little bit better. So it's a 100 baud 4 FSK protocol. It's got a 32 byte payload, and that includes latitude, longitude, timestamp, altitude, speed, some GPS telemetry, temperatures, internal temperature, battery voltage, and then you're also afforded 9 bytes of additional telemetry data, and you can customize that. One of the boards I've laid out, this little guy here, this is a Bosch BME 690 breakout board, and this is just another environmental sensor that we can hang on our payloads, and that would get factored into the 9 bytes of additional telemetry there. This at 100 baud with all the FEC and everything, it takes 3.3 seconds to transmit a full packet, and it only occupies about 1 kilohertz. This is with a 270 hertz tone spacing. This is very significant because we run this continuous on a specific channel. We'll move this into the 432 spectrum, away from APRS, away from everybody else, and it's awesome being able to have continuous data coming through this pipe without the fear of the old APRS goats pitching a fit about me beaconing every 15 seconds. I have received hate mail before for running 15 seconds on balloons on APRS, and it's easier just to stay away from that network. I mean, the guy was in Texarkana too. It's not like there's any other traffic out there anyway, but whatever. So why run a 100 baud 4FSK protocol?
Good one.
Um, it's got a much higher noise immunity. Over 1200 baud AFSK, there's about a 20 dB advantage. And based on just kind of gut instinct and field testing, I would argue that it might even be higher, maybe close to 23 or 26 dB advantage over 1200 baud AFSK. And that's assuming I transmit at 50 milliwatts with one of these trackers, it would be equivalent to what would that be? Almost 5 watts, maybe even 10 or 10 or 20 watts APRS. I mean, it's just very impressive what you can get away with this protocol. You can also, because it's got such a distinct noise advantage there, it can be received with effectively a wet string. On my truck, when I'm chasing these, I run a quarter wave mag mount. It's just an NMO mag mount with a quarter wave UHF antenna on it, and that's it. It works great. The only disadvantage of this protocol is that it is received with a sideband protocol. So you need an upper sideband capable radio on UHF. There's also fewer ground stations. There's fewer eye gates because we have to stand them up specifically for these launches. So you don't have the robust APR, if I can talk, the robust APRS network as is. So what is it supported on? How do you transmit these? Well, we use the Vaisala RS41. That's a radio sonde, and if you've got your display set up right, this is it right here. I'm holding one. We collect these from the National Weather Service. They launch these twice a day out of the forecast office in Fort Worth, and the text on that sticker there says, "Please don't return this. Congratulations, but we don't want this back." So it's a harmless weather instrument, and yeah, just please dispose of this properly. So in the picture here on the slide, this was a marathon day where we collected 8 of these last year sometime. These radio sondes transmit temperature, humidity, and GPS data. And from that, you can derive and interpolate all the other data you need to feed your weather forecast models. So that's our go-to tracking platform. Other groups or other parts of the country don't fly Vaisala, they fly GRAW. The DFM-17 is an equivalent piece of hardware, but just from a different manufacturer. But it is also fundamentally a radio sonde with an STM32 in there. And real quick, I'll show you what that PCB looks like. This is it here. I've got Amazon batteries in there for the purpose of a Fox, and you can see on the backside here I've got the Fox label, but this is just an STM32 with a Silicon Labs radio IC in it, which is perfect for reprogramming as a tracker. There's Arduino reference code published, and then there's another guy that's actually building his own tiny tracker, the Tiny 4FSK. But at the end of the day, this protocol is open source, and anybody can build their own Horus binary tracker. So how do you actually fly with it? It's real simple. Step 1, you obtain the radio sonde. That's done via sondhub.org. We've stood up a bunch of receivers to actually monitor the ones that the Weather Service launches. They transmit in the 400 to 406 band. So we go and we collect them out of fields, out of front yards, out of backyards if people let us. We just pick them up everywhere. Step 2, obtain a Horus ID. Similar to DMR, these don't actually transmit a call sign. They transmit a 16-bit ID, so you have to get that allocated, and it's just as simple as asking for one. You flash the firmware on there. RS41NG is the firmware, and then your standard ST-Link V2 with a custom cable is all it takes. And then finally, you launch it. So how do you actually receive this? And this is the part that I really want y'all to pay attention to, because I expect to see every one of your call signs on the log. It does show us who actually received these packets. So pay attention here. It's very easy to do. You'll need the 432 megahertz upper sideband radio. This is an RTL SDR, it's an FT817, it's a 9700, it's any radio you're familiar with. But it's also the cheap Chinese $25 Quansheng UV K6. So you probably can't hear it over my microphone, but the zoom filtering's pretty decent, but if I could share my audio from this radio, you would hear the 4FSK tones. But this radio with some alternate firmware will receive sideband, and it does work very well for decoding this protocol. Let's see. How do you actually receive it? Well, there's the Horus, Web Horus, they call it. And let's see. We'll go over here. This is Web Horus here, and just horus.sonthub.org. And this is actually a web-based decoder. This will receive the packets. This is actually receiving a transmitter that's out on my back patio right now. And all you do is allow your browser to pipe in mic audio, and it will receive everything. It'll decode everything, and you can tell it's decoding because these cards will update. You can see new ones will flash in here on the left every 3.5 seconds as another packet is decoded. So this is it working right here, and this is it working very well. It's also got a little map, and you can see, here I am in the Richardson area. We'll zoom in, wait for the next packet, and it'll center up over my house there once it gets that next packet. It's also got some plotting here, so you can see some of the telemetry. You can see the altitude, just that jitter off of the GPS, but it's also got other parameters there that are being plotted. So anyway, pretty cool stuff. That's all in the web browser. It's stupid easy. The next method is Horus GUI, and that's actually what I'm showing right here on the slides. I've got this running on another window as well, but this is it. This is a program, an exe you can download from the internet. Same thing. It supports all of your sound card input, but it also supports a UDP audio input. So like over here in SDR++, this is that radio sound on my back porch, and I can tell SDR++ that I want to send out the audio via UDP. So it should be doing that right now. Stand by 1 second. I'm going to change this receiver over here. So here is that Horus GUI receiving audio via UDP on the network. So at the end of the day, this is just a very quick and easy loopback mechanism instead of a virtual audio cable. So UDP audio is slick. I like it, but this is kind of the best way to do it with an RTL SDR dongle or SDR Play or anything else that supports GQRX or SDR++. The other kind of curious thing about Horus GUI here is that it's got rotator control. So I can connect it to anything running rope controlled D. I can, tell it to go somewhere, and it will keep my satellite station pointed at the balloon as it's flying aloft. So the last method, and this is for the advanced users in the bunch, and I imagine most of y'all could figure this out, but it's using Horus DMod library, and this is just a set of shell scripts and Python and whatnot that runs on a Raspberry Pi. This is kind of the most headless and most robust method to do this. This is what I run in my truck when I'm chasing. I've got a Raspberry Pi that sits in the center console with an SDR Play, but that's kind of a little out of scope for this talk right now. So let's talk about where this gets displayed. This goes to SoundHub Amateur. And SoundHub Amateur is like APRS.FI, but it's designed specifically for high-altitude ballooning use. It provides you a mapping interface. It provides chase car support. So I can click a button on SoundHub Amateur and say, this is where I'm at, and continuously upload my position based on, APRS packets. If you actually want to do it via APRS, you can just add SHUB in your APRS path, kind of like another digipeater, wide 1.1, wide 2.1, and then SHUB. But anyway, it's very good for APRS type functionality to know where the other chasers are, but from a web browser and not via APRS proper. It's got a very robust telemetry display, and let me see if I can pull that up real quick. We go over here to SoundHub Amateur. I'm going to find a different balloon that's flying just Yeah, we'll go over here. This guy, I don't know who this is, but this guy launched earlier today near Rapid City. What is that, Iowa? But it's got these Grafana plots. So it's just a really nice visualization of everything on board, right? You got pressure, temperature, you've got ascent rate, descent rate. You can know who picked up all the packets. Anyway, they've done a very good job integrating this with Grafana, and I highly recommend checking out SonTub Amateur for that telemetry display. They also provide real-time landing predictions. Using the NOAA GFS model, and for whatever it's worth now that there aren't as many radiosondes going up, it does provide you pretty good landing predictions and kind of a good estimation as to where you should be positioned to collect this balloon when it comes down. It will also automatically ingest APRS packets that have the balloon icon, and it works very well for that. So we did already show the SonTub plots example. Let's see where this one points me, though. There might be a different launch. Yeah, this was one of our flights with the RWK tracker not long ago. But as you can see, we had a bunch of receivers here, a bunch of people listening in for this horse binary, but only maybe one or two NTMS call signs in that list. And I think we can fix that. So, what is Chase Mapper? Chase Mapper is very similar, but it's more specifically designed for local operation. I display this on my dash in the truck. I've got a nice Pioneer head unit that has an HDMI input, and so when I'm chasing, I run this, and it actually works very well. There's a way to collect local packets via UDP listener. So all the different decoders can broadcast packets via UDP once it's decoded. It supports that chase car position uploading that I was talking about. And most significantly, it's got real-time offline predictions. So every 15 seconds, it'll update where it expects that balloon to land. And on this image here on the right, I want to show that there's two traces from the balloon. The blue trace, which is if the balloon bursts at the expected altitude, and then the red trace, which is if the balloon were to burst right now. Ideally, those converge on the same point. Ideally, your balloon has made it to the expected altitude. But if it does burst prematurely, that red trace is showing you about where you should be positioned if it were to go now. It'll also provide you with a landing timer after burst, and this does factor in atmospheric density. So those different pressures at various altitudes and what that'll do to the parachute do get factored in to that landing timer, and that's really good for again positioning yourself to watch the balloon come down and being right at that landing site when it lands. And it can also use locally cached maps. So installing it is real simple. It runs in a Docker container. It installs easy on most operating systems. It runs headless on a Raspberry Pi, but it also works well with a display. This picture on the right shows the setup that's in my truck. It's just a like 4.3-inch touchscreen on a Pi. There's a little GPS receiver there. There's the Newelec SDR and a Raspberry Pi branded USB hub. This is all you need to actually decode all the different modes I've been talking about so far. You can also display it on the dash with a tablet. So let's talk about WeNet. This is the end-to-end image transmission protocol. So this collects images via a Pi camera. We've been flying the Pi camera V3 wide, and we really like it. It'll resize, it'll add overlays, and it'll compress the images using the SSDV protocol. Once it's done that, it transmits it down via 115.2 kilobaud link. It uses a LoRa radio, but it does not use the LoRa protocol. It actually feeds the UART pin on the Raspberry Pi into the direct modulation pin on the radio. This is known as direct or async mode. It uses LDPC for about a 6 dB coding gain, and its legitimate like spectral use is about 300 kilohertz. You can see there in that video that it is pretty wide, but it's not terrible. It does fit within the reasonable spectrum that we're allowed to use. So what does this actually look like? I've got two transmitters shown here. The one up on the top is the one that the Australians fly, and then the one down here on the bottom is mine. But I've also got a slow scan TV radio there as well, and I'll show you that here more in a minute. Raspberry Pi 3 or newer, the LoRa RF hat, the Pi camera, of course, U-Blox USB GPSs. The U-Blox GPSs work very well at altitude. Some GPSs are questionable if they support it, support running at higher altitudes, but the U-Blox GPSs do allow you to unlock them as long as you don't exceed a specific velocity. And then my preferred method, I use faucet covers and 3D printed bases. And so this here is the faucet cover. It's got some branding on there, just the SonTub logo, some RWK contact information. On the top, I 3D printed a cap to go in the hole. There's also the hole for the antenna. And then on the back side here, I've got a sticker with the weight so we can know how much this is going to weigh when we're factoring in payload weights. The actual payload itself here is a bit of a mess. This Velcro straps the faucet cover on. This antenna is not the actual flight antenna, but it has flown because other antennas have broken. This radio here is the same Quansheng I was showing you earlier, but it's connected to the audio output on the Raspberry Pi, so we can downlink slow scan TV. And this radio just runs the standard battery that comes on it. The Raspberry Pi is powered by 8 Energizer Ultimate lithium batteries. So this looks a little kludgy. It looks like a mess, but when it's all put together, it's actually pretty solid. This just doesn't have problems. It just works. So that's how we send images in real time. Building a receiver. Also need a Pi, RTL SDR dongle. You need some antenna gain. This only runs at 50 milliwatts, and you will need some antenna gain because it's so wide band. Usually satellite stations or better are what I would recommend for this. There's a Docker image that has all the software to receive it. It'll talk directly with your RTL SDR dongle on a Pi, and it'll upload the images to ssdv.habhub.org so you can watch it in real time. There's also a new method that I want to point out, and that's wnet.sonthub.org. And very similar to that web Horus decoder, you can actually interface your RTL SDR to a web browser, and it's a genius implementation, and it'll decode it there in the web browser for you. So I would recommend checking that out if you don't want to go down the Raspberry Pi rabbit hole. So additional features that WeNet offers, it can send GPS data to SonTub Amateur. It can provide image data, of course, and the image is composed of many packets. So say I receive half of an image, and then the receiver I've got up at TWU receives the other half of the image. These two can be recomposed, reassembled by ssdv.habhub.org. All the packets are small enough that it'll just reassemble them almost like an analog voting network. It's actually really cool. So with a distributed ground network, and especially with geographic diversity, as the payloads swing, you might wander into an antenna null, but another station might be at the proper or peak location to receive, from that quarter wave antenna we've got on board. So it's pretty cool. You can get whole images, even if all of us only receive partial images. The whole image can be displayed online. Another interesting thing that we're planning on doing, and we've tested this, but it hasn't worked great yet, that's telemetry aggregation. And so actually on the payload itself, there's a UDP listener. So other payloads like a Raspberry Pi Pico W, like this guy right here, this can connect to the main payload, the big WeNet payload, in the faucet cover via Wi-Fi. And then this via UDP packets can send telemetry like that you'd collect from a Bosch BME atmospheric sensor. there's also plans to do this with Bluetooth Low Energy. So this allows like student payloads and other, low key payloads that you don't want to engineer a whole downlink for to provide data and have it downlinked in real time. The Python to drive this is just so easy. So there's just so much potential with the idea of, you don't have to downlink all the way to ground. You just have to uplink to the WeNet payload here. So anyway, here's some images received by the WeNet payload and decoded in real time. This came from our launch in September, back on September 21st. And this was the last image downlinked before another payload sheared the antenna off of this payload. And you can see it's missing a couple bytes, a couple blocks down there in the bottom right corner. But this was received, or the image was taken just before burst, and then it was downlinked just after burst, and then we lost the antenna, and that was that. But what does a Horus-centric launch configuration actually look like? Well, a couple trackers, RS-41s running the RS-41 NG firmware. You've got your camera. It's running WeNet with a PyCam V3. You've got a receiver, and that's like a Pi 4, Pi 5 with an RTL SDR dongle. We use KA9Q radio to do a real clever FFT multi-slice receiver. So we can actually run 10 or 15 different receivers on one Pi at a time using a single RTL SDR dongle. The only thing is it has to be in the 2 megahertz span of the RTL SDR dongle. That's why we aggregate everything from 431 to 433. This runs Chase Mapper, so we can locally plot it. It uplinks to SONDHub Amateur and ssdv.habhub.org. So to run this multi-slice receiver, we use Docker Compose. And Docker Compose is just an orchestrator of a number of smaller applications. So on the shell terminal here, you can see we're running a bunch of Horus binary receivers. We're also running Chase Mapper, we're running KA9Q radio, and we're running WeNet. So all this together really does a great job of receiving almost any payload we can fly that falls into this ecosystem. I've got this published on GitHub there at the K5RWK GitHub page. So what does this look like when it's actually implemented? Well, this is Tony, W5ADC's receiver, and this is on a roof rack on his car. There you've got a quarter wave ground plane antenna, you've got a preamp, and then in the box on the front there's a battery, a Raspberry Pi, the RTL SDR, a fan, and a battery charger. This is what it looks like inside that box. So really clever stuff. This is all Tony's 3D printed design. He did an amazing job looking at the thermals and everything else involved with this. And this was one of our key receivers at the GPSL conference last June, or this past June, a month ago. SONDHub also offers a really cool calculator. So this is what we use to figure out what payloads or what parameters we should use when inflating the balloon. We define our payload mass up here in the top left. We define the balloon that we're using. We define a target burst altitude or a target ascent rate. I personally I like to go with 5 meters a second ascent rate. That's approximately 1,000 feet per minute. Anything slower than that, and your balloons just take forever to go up and then come down. Anything more than that, and you might not be extracting the maximum burst altitude that you can. But most importantly, we're looking at the neck lift here. We use that when we're inflating the balloon, and we look at the volume, the expected hydrogen volume that it will take to inflate these balloons. More info. This is the last of these slides, but I do have some more things I'll show y'all. There's my email address, the Project Horus GitHub page. This QR code does link to these slides, so if you take a picture of that or scan that real quick with your phone, you can access these slides at a later date. And of course, SONDHub and SONDHub Amateur. This is kind of the core ecosystem for what we do with these launches. So I know that was a lot of information real quick. Do y'all have any questions? I'm not hearing anything.
Yeah, this is Doug. I want to know if that's Cat 6 or Cat 5 that was going through the picture.
That was cat one. The uh the black cat that wandered through there a minute ago.
Yeah.
Yep, the shadow cat. Yeah. No, cat number one.
Hey, Andrew, this is West of A5TKU.
Yes.
Curious line the frequency ranges that you're using.
Say that again, please.
I'm curious about the frequency range that you're using.
Yeah, so the frequency range we're using, we chose that because it's the kind of experimental part of the band, low power, digital. I forget exactly what the AWRL specifies, but yeah, that's why we chose that part of the band. It just happens to coincide with the beacon over there on TWU.
Yeah. Well, it also covers the 432.1, where most of the sideband activity and around that same area, the digital activity on 432 are by
Correct.
individual stations. So,
And we don't run anything from 432 to 432.5.
yeah,
We
but you also, it goes as you discovered the beacon that interferes with you.
The beacon
Uh,
does interfere with us, yes.
But
But
a single station could interfere with you too.
it
Some of
is
these,
possible, yeah.
uh, there's some fairly high power around 432.
So let me show y'all some other things here. We'll talk about payloads in just a minute, but this website here, predict.sondhub.org, allows me to specify some launch parameters, and it will give us a predicted flight path. So in this case, I said, tomorrow at 9 o'clock, I want to launch from Salina. We'll say the balloon goes up at, I don't know, 5 meters a second. We'll say it comes down at 5 as well. And this looks like a pretty decent flight heading out over Lake Ray Roberts and landing out there near Roston. So this tool gives us a good idea as to what our flights will be doing, and you can do these up to about a week in advance. So if I were to say on July 19th, it looks like it's almost the same trajectory, but we use this to really pick out our launch sites, and actually we pick our landing site and then choose a launch site based on that. We did talk about Chase Mapper. Probably don't need to cover that any further. I'm going to go through some pictures real quick from some of our previous launches, and here you can see Doug, but of more interest is this station right here, and this is a small satellite rig on a tripod. And in this box is one of those receivers that I was showing you. It's got a Yaesu G5400 here. There's a GPS inside this box, and this will stay pointed at the payloads pretty well at all times. It just decodes those payload positions, it does some trig, and then it figures out the ideal look angle for it to actually stay pointed at the payloads. This works very, very well. This is how we maintained WeNet reception until we get high enough that the ground infrastructure, like the satellite station at my house or at Chip's house or at UTD, can take over. This was another launch here. This was a week later with some leftover hydrogen, and yeah, you can see kind of the same setup here. We had the satellite station over there behind Alice. There's our balloon being inflated, and these pictures were transmitted in real time from that WeNet payload. This payload right here in front of us is just an RS-41. This was funny. This was a flight of leftovers. So we had leftover hydrogen, and we wanted to use it before we had to return the tank. And our lift was not what it needed to be because we didn't have any extra hydrogen. So we actually removed the parachute from this flight. It ended up not being an issue, but it was pretty funny. But yeah, you can see we started getting some pretty cool photos here at altitude. I'm going to scroll down here towards the end. And so this was the last in focus picture we received from this before the balloon burst. Pretty cool. I like this a lot. And contrary to what the flat earthers will tell you, this curvature of the Earth is real. It is observed, and we have seen it with our own payloads.
How much are the balloons, Andrew?
The balloons, it depends. Usually between 100 and 250 bucks, depending on what you buy. I've spent as much as $425 for a balloon, though, and that was a high altitude attempt that actually didn't make it up and break any records. Kind of disappointing. This particular landing was in a tree. Every landing is in a tree. It's inevitable. And this one was pretty easy because it was on the side of a tree. But there's that RS-41 sitting right there, and then the WeNet payload sitting right under it.
Andrew, how do you interface with the FAA?
We don't. The FAA doesn't care what we do as long as we stay out of Class B airspace.
Sorry. So as a private pilot, I take off. I'm tooling across the lake there, whatever. There's no deconfliction going on.
Nope.
No, you're there.
They don't know we're there, and there's no deconfliction. And as long as we fly within specific weight and payload density requirements, we're okay. We can't have more than 12 pounds of payloads on the string, and there's density requirements as well. But the FAA just has calculated that the risk is just insignificant as long as we stay within those parameters.
I guess it's all statistics, but I can tell you a 12-pound bird coming through the windshield of my Cessna is going to disappoint me a bunch.
For sure. And that's why the density requirements exist as well. And, each payload, I mean, it can't be 12 pounds. Like the payload I'm holding right here weighs about a pound, and the other payload that Tony's about to pick up there weighs 90 grams. So we try our best to maintain that kind of separation of weight. So what does come through your windshield is only maybe a pound or two. And hopefully it doesn't even come through the windshield at all, Right.
I guess it's just that I would guess the other thing is it's kind of like the deconfliction of all the drone traffic.
Sure.
There isn't any that I know of.
Mm-mm.
So around airports, there's no limitation on where you can launch.
And Class B airspace. I'm not allowed to fly into Class B airspace.
Sure. Well, there's a lot of airspace around here that's not Class B, and certainly B or more, right? So going into Bravo is a big deal for Dallas-Fort Worth. But when you're out here in the hinterlands, it made me wonder, because you got all this communication capability and GPS coordinates.
I have to find a logbox for my beef organs.
Planning,
I'm gonna have to
where
find a
it's going to
logbox
go.
for my beef organs.
Yeah.
Look,
There's some other interference there.
Scott's got an
they
open
smell
mic.
it and they're meowing for it. I'm gonna have to find some place to lock it.
So we did actually have a pilot fly into Gainesville to watch one of our launches, and he was joking about chasing the balloon with his plane, but he actually worked our DMR repeater through.
Pilot smelled it before I opened it. Before
right.
the seal was taken out.
Can y'all mute that mic? Is that a thing?
Hey, Jim, can you mute Scott?
I'm sorry.
There you go. Don't worry.
So we did have a pilot, actually fly into Gainesville to watch the launch. He used the airport courtesy vehicle to come out to the launch site. And then once we finished, he went up and actually made contacts through our DMR repeater while he was airborne. And that was pretty cool. And I guess I'll take a moment to talk about that real quick. I'll show y'all what the DMR payload looked like. And this is it right here. It's a Hytera PD982. This is a quasi-commercial DMR radio, and all I had to do was buy a $100 license for this. And so y'all don't strike me as the DMR type of crowd, but for those of y'all that are familiar, it's just simply listening on time slot 1 and rebroadcasting your transmission on time slot 2. For the non-DMR crowd, DMR is a TDMA mode, and so when you're transmitting to a DMR repeater, you're only occupying about 50% of the available time. There's two time slots, time slot 1 and time slot 2, and this payload leverages that TDMA nature to do a really clever thing and serve as like a real-time parrot repeater. So you program your DMR radio to talk on simplex, so just take your Motorola TYT, whatever DMR radio, 441.0 simplex with all the right talk group settings. You key up, this hears you, and then this rebroadcasts that on the other time slot. And it's genius in a number of ways, and the most genius way that I think is the fact that the user, you are the timing master. So this repeater radio only transmits when when it doesn't hear you. So there's no sync issues or anything like that, because this is only transmitting when it's not hearing you. So you don't run into delay issues. Standard DMR through repeaters is limited to like 125 kilometers, but this doesn't have that problem. And we've had Houston talking to Wichita Falls and Texarkana all through that DMR payload before. So let me share my screen again and kind of keep walking through some of these slides here, these pictures.
Anybody mention Mesh-tastic?
We have not done Mesh-tastic yet. And I keep saying all we need is for someone to build the payload and convince us that it has value for either ham radio or like reasonable experimentation. So if it's cool, built, and something we can legally fly and does add value to the hobby, we'll definitely look into that. But on this slide or this picture, what I want to point out is that the balloons will inevitably land in trees. Before this flight, we were warned that there was a nudist camp in the general vicinity of this Hutchinson, Kansas conference, and this landed literally across the street from that nudist colony or camp. They're like, hey, by the way, if it lands in this little square there, that's nudists, and avert your eyes. But literally across the street from them is where this payload landed. I thought that was pretty funny. So let me kind of show y'all what the launch process looks like. So we'll lay out a tarp. We've got our balloon there. It comes in a bag. This is a 4,000 gram balloon. This was for a high altitude attempt. Its only payload was this 90 gram RS-41. We've got our hydrogen tank right there. Its nominal pressure is 2,400 PSI, and that will expand out to 300 cubic feet when it's all said and done. Let's see here. So what we do is we put 20 pounds of weight on a scale, we zero the scale, and then anything we pull up will read on the scale. When this balloon was fully inflated, for the amount of lift we wanted, it wasn't fully expanded. There was still some kind of slack in the balloon, which I thought was pretty interesting.
Why the barbecue gloves, Andrew?
Why the barbecue what?
Why the barbecue gloves are on?
Oh, the barbecue gloves. It has been alleged that the oils on your fingers can possibly degrade the latex prematurely. And to extract that last 0.1% of performance out of the balloon, we put on the nitrile gloves. But I don't know if it actually makes a difference, but it's accepted practice in the ballooning community, so we run with it. But yeah, there's the balloon up and away. We didn't even have any string between the payload and the balloon. We just sent it up exactly like that. And it flew for almost 4 hours. But the issue on this one, the balloon reached a super pressure state. It turned into a floater. The latex just stopped expanding. And what I was hoping for 137 or greater 1,000 feet. But this one leveled off right at 120, and it was a very expensive attempt to break a record, and it just didn't do so. So
Why
let's
not
see.
use a Mylar or something?
Those usually level off around 40 or 50,000 feet. My goal was to beat this guy's high altitude record, which was 137,000. And the running joke is that since he helped us inflate the balloon there, that he might have, punctured it or something.
Sabotage.
Yeah. You can't trust those old guys, those old gray hair guys, I realize that that's most of y'all on the call. So this was our second, or actually the third balloon of the day. The first one was the one that landed in that tree. That was launched into a thunderstorm. It got sucked into a hail core. The hail core punctured it, and then it landed right by the nudist colony. Balloon number 2 was the high altitude attempt. This was balloon number 3, and I don't have a good picture of it, but um, there's a handful of payloads here. There's a 360 camera that's below the parachute and above this tracker, and that detail is important. Remember that. Parachute, expensive Insta 360, $500 camera, and then first tracker. Then we've got the second tracker behind me, and then the WeNet payload is sitting on the park bench right there, taking pictures of us as we're inflating our third balloon of the day. Little distraction here. These are some Mylar floaters, just like David was talking about there. These ones all will level off at between 40 and 50,000 feet. They don't expand and burst like the latex ones. Let's see here. Balloon's about ready. It's almost fully inflated there. We had to switch to our second hydrogen tank because there was a lot going on. And then we do what's called a tethered launch. And so Alice here on the left is holding one end of the string, and then it goes up through a pulley that's situated right under the neck of the balloon. And then Sammy here is holding the other end of that string. And when we're ready to launch, Sammy will let go of her end. It'll feed through that pulley, and then the string will fall down. The paracord will fall down, and all the payloads will go up. This was another launch. What these guys did is they just had everybody hold their payloads palms up, and they just let go of the balloon, and up and away it went. There's Sammy holding her end of the string there. And real quick, let me might have to refresh this page here. Dang, I added a video to this. Let me see if I can find it real quick. This one. So I was talking about, pay attention to where that camera, the expensive camera situated right here above the tracker. Actually, sorry, we'll get back to that detail in a second. This was the tethered launch, a video of it. And when we let go, you can see the balloon keeps going, but our payloads are not going up. And the response from the audience was, ooh, and then, oh. And then it promptly lands in a tree. All right, that's inevitable, right? The yellow, like, mason's twine that we used for this had degraded. It's probably 10 or 15 years old and had sat in the sun, and the friction from our tether when it released was enough that it actually burnt through that mason's twine. And so up goes a $150 balloon and about $75 in hydrogen, and our payloads immediately come back down. So that was real nice. I wasn't too happy with that, but such is life. So now we're inflating a borrowed, horse traded for balloon. This is balloon number 4 of the day. And we hadn't identified that yellow twine as an issue. You can see we're using it again here. So
Why
we get
not just use paracord, or just because you had so much of that twine laying around?
We had a lot of that twine laying around, and paracord does not meet the FAA spec for braking strength. It's a 50-pound limit. Paracord far exceeds the 50 pounds that that it must brake under.
Okay.
Here you can see that Insta 360 payload, the fancy one. So anyway, this goes up. We get this one off the ground. This is the last photo I have of this launch, but we get this up off the ground. It takes some amazing photos, and it makes it up to about 45,000 feet, almost 50,000 feet, and then it comes back down. And we're like, the borrowed balloon must must have punctured or broken a little early. It must have burst well before we intended it to. Um, when we recovered the payloads, this was missing, but we found this tracker, the next tracker, and the final payload. So this Mason's twine right here broke, and now sitting somewhere in a field in Kansas is a very expensive camera. And I'm hoping that someone can see my name badge that I'm wearing in these photos, in this video on that camera, and mail it back to me. But I'm not holding my breath for that one. So anyway, we also got stuck in the mud in the chase. You know, you don't really realize how deep you're in until you're like stuck. Here you can see the FJ pulling us out, and then the anchor truck behind the FJ. This was actually pretty entertaining. It was a fun experience all around. But we had a great time despite all the issues with the launches at GPSL at this event. We did have a great time. The last set of photos I want to walk through are back here. This is our launch from a week ago, out of Salina. And we made some process improvements here. Most importantly, we kept the hydrogen and helium tanks in the truck, and we ran an air hose over here. It's nice to not have to wrangle that 150-pound tank and get it out on the ground. We replaced all of that sketchy yellow Mason's twine with some actually tested stuff, and it worked a lot better. Tony, W5ADC here, 3D printed a little mechanism that sits in the neck of the balloon, and he puts a check valve in there. So we don't have to actually take the balloon off the fill mechanism. We just disconnect this coupler right here, and this whole thing flies with the balloon. And that reduces risk. The chance of us fumbling the balloon and letting go of it are much reduced if you can have the payloads fully attached while you're inflating it. Here's a close-up of that mechanism. You can see the check valve there and the rest of the 3D printed neck mechanism. Alice and Sam helping attach all the payloads. On this one, this payload on top is another RS-41 tracker, but in this case, let's see, I've got it right here. I 3D printed a case so I could use a much larger battery, much larger than the AA's that usually go in there, because I got tired of buying Energizer Ultimate lithium batteries. So 3D printed a case, and I'm using a Maker Focus lithium-ion battery. This next payload in the string is the crossband repeater, and I'm working on 3D printing a case for that. I don't know if y'all can see my video here, but there's the crossband repeater radio, and I'm doing some test fits as I'm working on this. Eventually there'll be a spot for the batteries under here, but those are just these two faucet covers, stuck together, radio inside there, and away it goes. So anyway, that was our payload string last weekend. There we are inflating it. Here's what the launch actually looked like. In this case, we didn't do a tether. We did the palms up launch, and we just hold the payloads all palms up and then let go of the balloon, and away they go. So let's see here. This was really cool. We got to watch the payloads coming back down. The prediction software was good enough that it got us in the right zip code, and Alice actually spotted these and alerted us that they were coming down. And I don't know how well y'all can see the screen, but those specks there, those are the payloads, and we got to watch that come down. Pretty freaking cool. Here's the recovery group. I was on the recovery team, but I didn't jump the last fence. These guys ran out in the field and grabbed it. And for the first time in a while, these actually landed in a field and not in a tree. The running joke was that all the trees were taunting the payloads, but the payloads couldn't decide which one they wanted to land in. Some pictures from the actual WeNet payload. I'm going to scroll down a little ways since this is all of them. So yeah, really cool photos there from the edge of space. There were some storms happening while this was in the air, just rain, but it was kind of cool to see those from altitude. And anyway, usually when the pictures stop leveling off and it turns into chaos, that's when the balloon has burst. And um, I know we've got pictures of the yellow string here as the post burst chaos sets in. So anyway, there was one really cool set of photos here where it comes through the cloud deck. There's actually two layers there, and I just think that's awesome. So anyway, in a nutshell, that's what we do. Um, that's that's ballooning. I know that was a lot of information really quick. Um, let's see, Chip, what have I missed? What do I need to discuss further?
You need to not so subtly invite them to put a payload in the next balloon.
Yeah, okay, about that specifically, when are y'all going to have a 1296 and a 10 gig beacon ready for me to fly so we can start getting y'all in on all this? Who wants to do that? The silence is deafening. Yeah, so what I would like to see, we've been talking about these RS-41s. This this runs at 400, about 500 megahertz, and that would be a perfect IF into an up converter. And then it can run this Horus binary protocol, which is easy to receive and should be pretty robust. I mean, we could also run CW in there too, but I would love to see Horus binary on 1296 or even, 10 gig. So I don't know. We are always inviting y'all to fly things. We kind of want to stick with a weight limit. 500 grams is about what I'd like to stay under. But let's discuss and let's come up with a payload for y'all to get on board.
Andrew, can you talk just for a second about the environmental requirements to do what you just said?
To launch the balloon or to fly a payload?
No. What the payload has to go through with those kind of altitudes, temperature, pressure, et cetera.
Pressure, assume it's going to experience a full vacuum. I say full vacuum, but 10 millibars, that's almost a vacuum. Temperature, negative 20 Celsius is about what I design around. Usually the only thing that'll impact is your batteries. Most COTS parts are negative 40 to plus 85, but negative 20 Celsius is a good target number. And that's what we usually measure on these when they're coming back down. That's when we get the most air running through them. And it really boils down to, the batteries, keeping the batteries happy. In terms of runtime, 4 hours is a good target. You need half an hour to 45 minutes on the ground before the flight, 2 to 2.5 hours in the air, sometimes up to 3 hours if the parachute is fully functional, and then a little bit of time after that for the recovery process. But 4 hours is your desired runtime. And then power output, man, that's up to y'all. I could do the link budget and everything, but I don't have the means to do that right now.
Well, the neat thing about this solution is that with the tracker software, you basically get a 3D, direction to point your antennas.
Mm-hmm.
So you can use high gain antennas to point to the payload because the tracker basically gives you that direction pointing. So we're not having to worry about Omni, and you can use high gain stuff. That's why I thought it would be perfect for something, very high frequency.
So like back over here on SondHub Amateur, let's see here. So I'm going to click on this balloon that's flying out over almost Nashville. Let me see if I can get this to zoom in a little bit. Up in the top right corner is an azimuth and elevation. So if you click on the balloon, if you allow your browser to provide the geolocation data, which as long as it's within the same zip code, it should be good enough. It will calculate your actual look angles there. Obviously below the horizon, we're not going to be able to see this balloon. But when they're overhead in our area, you shouldn't have any problem. This one's, a bit of a, don't trust that elevation angle because we're effectively at the same location. But yeah, that's how you can point your antennas if you've got full ASL control.
So what are the guys doing that end up making them go all the way around the Earth 2 or 3 times?
They fly what we call floaters or pico balloons. And so they'll design a payload that's usually nothing more than something like the Pi Pico here, a tiny Silicon Labs radio. They'll use magnet wire as an antenna, and they'll usually do like a 20-meter dipole and just run whisper. And so they'll fly this under a Mylar balloon, party balloon type of situation. But we will use like 1,000 times more hydrogen in a single one of our launches than they do with one of theirs. And when they're inflating their balloons, they're measuring it in like inches of water, like under 1 psi. Our stuff is measured in several psi.
Same kind of altitudes?
Different altitudes. Theirs will level off at between 40 and 50,000 feet. And this launch, let me share my screen again. This launch out of Nashville a little while ago, it's actually a really good example. So this guy launched earlier today. This is a floater, and I enabled the float mode here on SonTub, so it does these predictions. But if we look at the plots here, or just this little icon right here, you can see how the altitude leveled off. And let me click on plots. Yeah, so you can see how it's leveling off right there at about 14 kilometers. He's likely using Whisper or maybe even APRS for this. Probably Whisper, though. Yeah, it says Whisper 20-meter Pico balloon. And it's got solar panels on board, so no batteries, and it just keeps running.
So they take winds aloft, predictions or measurements in order to know where it's going to go?
Yep. And SonTub Amateur provides you with that. That's what those traces going out, up over the Atlantic were. Those are the predictions with where that balloon may go based on the GFS model.
I'm quit asking all these questions, but what makes it come down?
The floaters,
Well,
actually, I'll start with our latex balloons. They simply burst. The balloon the latex will shred, the balloon will burst, and it comes back down via parachute. It's also recommended that you fly a cut down device. We typically don't because the balloons will inevitably come back down. The floaters, if they're going to come down, usually it's a thunderstorm. If any moisture accumulates on the balloon itself, condensation or ice crystals, that's enough to weigh it down to the point where it'll just touch down. The other thing is a leak. If they don't perfectly seal that Mylar balloon, hydrogen can leak out and it'll cause it to come down very slowly, but it will come down.
Why do you fly hydrogen instead of helium? Price
And more lift. So for me, I've got 4 tanks of hydrogen in my backyard right now. The actual tanks were donated. And so for me to go and swap one of these bottles for a full one is going to be $70. And that's good for about a flight and a half. For me to fill up a tank of helium is going to be about $650.
So the trade is any danger. All I know is the Hindenburg didn't do so well on hydrogen. But
but so far we've avoided the Hindenburg 2.0, and we don't have a flammable paint that we cover the latex in, and that tends to help a little bit too. We do follow some safety protocols. We do only handle this outdoors in an open area. And hydrogen has the distinct advantage, and the only reason we really handle it is because it has lift, right? It has less density than the rest of the air around it. And so it dissipates insanely fast. you don't have to worry about it in the same sense of like propane or natural gas or other typically flammable or explosive gases that you can come in contact with.
The explosive, you need to be at least 2% hydrogen in the atmosphere for, for you get the bang.
Yep. And, the tanks that are ratchet strapped to my fence in the backyard, open air, no ignition source around them. And if they need to dissipate, I mean, it's easy to dissipate. I've got another tank in the back of my truck right now from our launch last weekend. And same thing. I've got a bed cover, but it's not a good seal at all. And I also remove all the potential ignition sources back there. So there's just minimal chance for it to actually cause problems.
You seem like you're having too much fun, and I keep thinking there's going to be an OSHA guy show up, or like
Yes.
the FAA, or somebody else is going to come over and try to rain on your parade.
Yeah, and there's some pretty reasonable rules we follow for ourselves that help avoid that, right? Just in how we handle the gases, staying out of the Class B airspace. If we do see something flying overhead, we'll hold off on launching for a minute because we don't need any issues with the aircraft, right? We used to file NOTAMs, but the FAA just seemed downright uninterested in any of them. They're like, "Oh, it's y'all again. Why are you calling us?" So after, I'm not going to say being burnt, but dissuaded by their attitude, a dozen times, we just decided that that wasn't really worth it.
Is there regulations say you ought to be filing them, though? Even if like to do it?
It's not a requirement. Some people recommend it. Some people, I mean, we've kind of converged on the it doesn't matter category.
I would have guessed there was some red guy that was going, you got to file another, and you're in violation and all that crap. But I think your other answer was really good. The statistics are such that you're never going to have a problem unless you do something ugly in heavy airspace.
Yes.
And the radar cross section, what you're doing is so small, unless it's Mylar, nobody's ever going to see the thing, right?
Yep. I mean, an AIM-9, what is it, the AIM-9 Sidewinder? One of those did manage to find a floater. And so there's like $500,000 of taxpayer funds that brought down a $50 Pico balloon back in the height of the Chinese balloon scare. But that was the only incident or recorded interaction we've had. We do think that an AWACS was scrambled out of Ellington to intercept something over the Gulf that other radio amateurs had launched. But no, otherwise, yeah, it's just not even a thing.
Well, I hope they don't find you.
Sondhub Amateur is out in the open, and if Tracon or whoever wants to pull it up and have it on their screen and whatever, they are welcome to. I do know that NORAD now cross-references Sondhub Amateur before they try and intercept a balloon. So we as the radio amateur balloon group try and consolidate all of our position reporting onto Sondhub Amateur. So NORAD is generally aware of what we're up to, but the FAA doesn't really take much of an interest in it.
So the other topic of your balloon bursts, and because of the material it's made out of, you can predict where, at what pressure, what altitude, what overpressure is going to tear it apart. So that's kind of how you don't end up having a chase that goes to the next continent. You can predict
Correct.
that material.
And, the National Weather Service, they launch 2 balloons a day out of Fort Worth, right, out of their Fort Worth office. And that is in Class B airspace, and they do have to call the FAA for that one. But the data collected from that is pivotal for us. I mean, it's the best that we could ask for because they plot the wind vectors and they collect all sorts of awesome data that feeds into the GFS model. And the GFS model effectively serves as a large interpolation method to figure out what our wind vectors will be at any given altitude. And so we can feed our data into that, or actually pull GFS data, run some calculations, and then come out with a predicted flight path. And that's going to tell us if it's going to go up in Salina and come down in Denton, or if it's going to go up in Salina and land in Shreveport. I'm not driving to Shreveport for these payloads, just straight up. So it allows us to make informed decisions before we even launch.
Cool. thanks for your answers. I appreciate it.
Yeah. What other questions do we have as a group?
Hey, Andrew, this is Scott A5AM. As far as the payloads go, what type of antennas do y'all run? Are they vertically polarized, horizontal, just whatever it happens to float around, or
What happens to float around? This right here is a quarter wave stainless steel wire, and this is what we fly on these trackers. Um, the the crossband repeater payload, wherever I set that, you know, this is a quarter wave on 2 meters and it's a half wave on 440. The WeNet payload, same thing. It's a quarter wave, a pair of quarter waves. One for WeNet, one for SSTV. I've wanted to 3D print a plate and cover it in copper foil and do like an inverted F antenna. I think those are pretty cool, and it would be pretty big for 432 megahertz. So we get more of like a downward facing pattern that's less donut shaped, no deep null coming off the bottom of that payload. But I haven't made it that far in my experimentation.
I have the PCB wheel antennas, which when they're off the flat side tend to be circularly polarized.
Mhm.
And a lot of those have flown on balloon flights.
Yep.
Not locally, but other places. And I've got those for 900, 1200, and 2400.
So the Houston group, the South Texas balloon launch team, they have flown your antenna on one of their DVB payloads. They've flown digital video with it, and it's worked very well. They did run out of gain, but that was on the ground side, not the balloon side. But yeah, no, I personally have seen them in the air. But on the receiving side, we just run the satellite antennas as best we can because they're circularly polarized, and that accounts for a lot of the sway. And having the geographic diversity is great. If you happen to be planted in the null of that quarter wave as the payloads swing around like a pendulum under the balloon. Chip, what am I missing? You've been along for most of this.
I don't know, other than it's been fun to fly what we've flown, but we want to fly new stuff. And that's one of the reasons I think we're here talking to you today. We want to push the envelope in terms of what we fly. And it just seems like this is a good fit. We're about cambered out, and we're about, crossband repeatered out, and we're looking for some new stuff.
Yep.
And are you aware of the group that has gliders with built-in control systems and memory enough? This is 15 years ago. I knew a guy at work, and they would balloon lift it, and then it was all autonomous, and it would come back to wherever it took off from.
I've seen people attempt that, and I haven't seen it work, but I would love to fly one of those if someone had such a payload for us. And I'm very.
It was a crazy stories that what he did at the altitudes he was going to.
Yeah, I mean, because our typical burst altitude is between 100 and 120,000 feet. So I would love to see how a glider, first descent rate, with minimal atmosphere, how it could navigate, how it could perform all the things, right? I think that would be awesome. But I just don't have the bandwidth to build that. I'm so booked just trying to get the balloons in the air to begin with, and just get all the trackers working and everything. But I would love to fly such a payload if someone had it.
These guys were all doing control systems for a living.
Yep.
So they're playing to do this.
Guys that know how to spell PID.
Among other things, yeah.
Yeah. And Kalman. How many L's? How many N's? Yeah. What else was I going to mention? So tomorrow, if any of y'all are interested, we are having what we call balloons and tea. This is at a place called Dubs Tea and Eats in Plano, and this is where we just get together on Sunday afternoons, 2 o'clock, and just BS about balloons. We're going to go over a lot of the past 8 balloons we've launched, because it's literally been 8 pieces of latex we've sent up since we last had one of these meetings. And we've been busy with field day and a bunch of other things. But that's where we cuss and discuss about balloons, talk about payloads. We're also planning on a launch probably in mid-August. The winds aloft should be calming down pretty well. If anything, they'll be pulling west by a county or two. But August would be our next target launch date. And I plan on having another 360 camera and some other things for that launch by then. And we'd love to have some beacon that caters above, 440 megahertz, if y'all have anything.
We have a sub list on our groups IO. That's a good way to stay caught up, Andrew. If you want to
Yeah,
put that somewhere.
Yeah, stand by a second.
For those of you that are on Discord, we have a pretty lively Discord discussion.
So I sent in the chat here on Zoom, I sent a link to our subgroup on groups.io. And let me send y'all the invite for the meeting tomorrow. And yeah, y'all are welcome to join the RWK Discord channel. As Chip said, we do have a bunch of chatter on there about balloons. We use Discord instead of Slack, but it's about the same thing. The other thing, I would like to apologize because I do turn off y'all's beacons up on Star Call at TWU when we're flying. I've got a receiver over on Gwyn Hall, and our spectrum allocation is pretty tight there. And I like being in the 432 part of the band, not far from y'all's beacon, because it avoids the commercial noise up in the 450 to 470 range very well. And despite tight filtering and everything else, I just couldn't quite notch out y'all's 432 beacon. So every so often, when there's a balloon in the air, that one might just be turned off, but it'll come back up by itself an hour or two later once we set that smart switch to turn back on. But I'll be sure to post on the NTMS list when we do have balloon launches, so y'all can be aware of why it's the beacon and not your receiver that's having issues.
Hey, Paul, can you get involved in this?
I'm sorry, were you talking to me? I wasn't paying attention.
Yeah, he was asking if you could get involved in this, Paul. I think he was asking if you want to build a 10 gigahertz transverter or, a payload for a balloon.
What I was going to show you what's sitting in front of me is a 24 gigahertz rig that is sick, and I'm working like a beaver to try to understand. But it does have good bandwidth and products. The thing that has bit me so hard as a physicist is that 10 gigahertz range scatter I found astounding, and that I could work somebody in Nebraska off a thunderstorm by Tulsa. So I think I'll put this in my cooking on list, because I think there's some really interesting blends of technology, and having something that you can lift to those kind of altitudes, I think is astounding. I've certainly watched a lot of engineering, but as a retired guy, I can tell you that the RF and the stuff having to do with how you get on 24 gigs with a watt is it's still challenging for me. I'm a guy that knows how to do laser things, and this is all new and wonderful. So yeah, I'll certainly be aware, and if I see something, I don't like it when anybody says, well, when I run out of something to do, I'll look you up, because I think you guys have something that's a whole lot more buzz and possible. It has a hook to get everybody interested in a certain way, but by the same token, the RF side is really what's kept me interested in topics. So I'll try to be aware, and I'll go out on your groups out and read, see what you guys are talking about.
Yeah. And, check out the RWK website as well, just k5rwk.org. We've got a bunch of balloon posts there. But a kind of question for the group, I'm just wondering about capabilities. What are the most popular bands that would be considered microwave? Would that be like 1296 or 10 gig or 24?
Depends on what you want to do. You want to bounce stuff off the moon is a little different than if you want to work Cropo.
Yeah. I guess the basis of the question is if I were to build, say, a linear transponder, classic, just copy and paste 250 kilohertz of spectrum from this band to another band, what would the input and output bands be to make it interesting? Like something high in and like 432 out, or, I don't know.
You do realize that the social history, because I've been around this for a few years, repeaters were not exactly looked on as everybody's friend. And certainly the satellite subcommunity has its own complexities. Not to say that there's not guys on here that haven't done all of that. I know there's interest in the microwave things of, like when some of the satellite guys or even foreign space people put things around the moon and other places, that certainly overlaps with a lot of interest. So where is the challenge of it? And I think that's why I asked about Meshtastic, because that's being a different technology, it's spread spectrum, and there's a little bit of knee jerk, at least for me as an old guy, about I don't necessarily want to learn more about computers. I know a bunch about them. I like them. I think they're cool. But if I have to choose between RF technology and more ones and zeros, I'll do some of both, but I don't go after that part of it as much. So maybe a way to ask the question is, what RF challenges fit within the domain of normal NTMS? And I'd be quiet about it and let other guys talk here. There's more guys that can speak to the spirit of it. But certainly weak signal work, how far can you actually talk? If your payloads were, when you look at, there's an app that shows if you put in your location and the other guy's location and height your antennas, it'll show you the curvature of the earth between you.
Yep.
Whatever. And I think it's astounding that even between where I'm sitting now and you guys out in Richardson is 40 something miles. And technically, if I went straight geometric line, it'd be 50 feet under the ground some places. So that's the kind of thing about what's available. And I think because of the balloon technology, you get such an advantage from the height part of it that I think you could do some astounding things with almost no power. And I think that's a different thing rather than the guys that say life is too short for QRP, right?
I guess another kind of idea, and I'm kind of curious what Al and like Bob are thinking as well on this, but should we fly an old school radar reflector? We used to fly those, so the FAA had better situational awareness of what we do, but you're talking about rain scatter, and I'm curious if a cubic foot, radar reflector would be enough that you could achieve a similar effect.
We actually had a chap up in Colorado try and blow out a cloud of chaff from a balloon.
Okay.
But at that altitude, it just came out as a big wad.
Yeah.
1 foot radar reflector is infinitesimal.
Yeah. I just wasn't sure what is the equivalent radar cross section of a whole thunderstorm. I don't know these things. I haven't done that math.
Well, you're talking about a cubic mile of little dielectric dipoles.
Okay.
Andrew, nice talk. This is Al. I would think that considering where all the activity is right now in the microwave world, at least terrestrial wise, probably a 10 gig beacon would be something that it would be interesting to see how far away you could hear that. And I think that most people, of course, they won't be aiming up at it necessarily. Well, I guess I shouldn't say that. Most people are just going to have systems that are going to be on the horizon. So I
Yep.
guess it would be interesting to look at, okay, if something's up at 100,000 feet, how far out is it going to see? It's probably going to see quite a ways, isn't it?
Yeah, I mean, our radio horizon extends down to Corpus, all the way up to Kansas City and Amarillo, sometimes as far out as Jackson, Mississippi. So that, yeah, there's a
And that's not allowing for atmospheric bending,
correct.
which we
All
see
the
which we see at 10 gig.
the balloons that were launched as part of GPSL in Kansas, when they got above the curvature of the Earth, I could track them here. I was tracking from 75,000 feet upwards. The 100 milliwatt transponder or transmitter
Yeah,
from Kansas.
yeah, 50. Yeah.
Yeah.
And so, real quick, I'm going to share another screen here. Just a note about atmospheric refraction. Um, So this here is a tool called Radiosonde Auto RX, and this receiver here is running up on Gwyn Hall at TWU. This is receiving between 400 and 406 megahertz, and its goal is to receive the radiosondes launched by the National Weather Service. And so these are balloons that it has received in the past 6 hours. So we've got the Amarillo one. Looks like Dodge City launched, and we received that. This one launched near Enid, Oklahoma, and then Shreveport's been launching as well, and of course Corpus. So the real curious detail here is this elevation column. That antenna up at 300 feet is receiving 7/10 of a degree below the horizon. And I know 300 feet versus ground level isn't enough to account for 7/10 of a degree, but that is 100% the atmospherics playing in at 400 megahertz. So I just think that's cool. I've
It's
had a
and it's more so at 10 gig.
yeah, no, I'm sure. But and this is kind of fun too because we'll see satellites come up over here in the 400 to like 401 part of the band. That's kind of like an ISM band for satellites, and we'll see carriers and LoRa transmissions and other things pop up down there. But this software just runs an FFT over that spectrum, and then looks for peaks, and then runs a scanning algorithm on the peaks. And if it can decode the right preamble for any type of known radiosonde, it'll spin up a decoder and just start receiving them here. But this is instrumental for us to actually collect radiosondes from the Weather Service, and then this software will then send it to regular SondHub. And that's one thing I didn't really cover well, but regular SondHub plots, where all the Weather Service balloons are going. And all these dots you see here are weather balloons that have been launched in June or July. And you can see how the wind shifted from out east to kind of coming towards the Metroplex, and then they're now drifting them out west. And then the dots that are filled are balloons that have either been recovered or we've attempted to recover them. And it looks like right now, Roger, AE5EZ, is trying to pick up this balloon. But yeah, so just side note, cool stuff that's part of our whole scheme.
I think you made a really nice presentation also. The interesting thing about your presentation is you pulled in a lot of different technology all together here in this presentation. Like the fact that you're using K9Q radio stuff was interesting to me too. I don't think enough people know a lot about that and realize the strength of that software that Phil has written. But the concept that was suggested about just using a beacon to start with, I think that's a great idea. It would teach, or we would find out, or people would find out about Doppler shift and things like that too in the tracking process, which is probably kind of interesting in this. And then water absorption or potential loss due to the vapors, I would think, could be interesting too.
What's the easiest way? I say easy, I guess two questions. What's the easiest beacon I could possibly fly? That'd be like a DRO or something. And then what's the lightest beacon I could fly?
Well, that's a challenging thing. I was thinking about there's a personal beacon project that Paul Wade put together that's pretty simple beacon, but it's got little copper pipe filters, which adds weight, you know. And I
An
think,
oscillator.
yeah, it's kind of like an oscillator, right? But you just key it on and off, and you got a beacon. And
I have a 555 timer, drive the VCC, and you get FM.
well, you could do that too. But you got, I think, more weight in that due to filtering or filters that are due to the way the thing is built and you would want to work with. But what is the weight that you would allocate to this beacon?
Somewhere between 500 grams and a kilogram to start, just that's like an unoptimized target weight. And then ideally, as we mature this, we'd want that to be smaller.
What his project was basically is like a 9x multiplier. And so you have to have an LO at like 1152 or somewhere in that range. So you'd have to build a board that had that lower frequency LO, and then you got this multiplier, and you got then your own 10 gig. So I'm not sure what that total weight could get down to, but to get down to a kilogram, I think would be a challenge.
And some of these synthesizer chips these days are crazy. I mean, TI's got parts that'll produce a 12.4 gigahertz like reasonable phase noise, just CW carrier for you, and it's crazy that that's where we are today.
Yeah, so then a dedicated board for this project could potentially get there too. That's another approach.
Yeah.
Question for you, Andrew. What if we were not circular polarized on the ground? Have you ever tried any tests just running linear to see how much it might rotate itself? Because all our antennas that we use terrestrially are circular polarized, and even on EME, excuse me, they're linear polarized and they're horizontal. And even on EME on 10 gig, we still run linear technology. So I imagine there's going to be a lot of fading.
Question for you. What type of cross-pole isolation are you getting? Like the standard 30, 35 dB?
No,
we're not looking. We're all linear on 10 gig.
Yeah.
So normally it's horizontal polarity for us and in the States.
I mean, so I guess the question is if you were to go from your horizontal to vertical pole, or if your source were to change polarity on you, do you know about what type of null you'd have? How many dB down?
maybe 20.
20?
Yeah, that's kind of the question.
Yeah. Okay. Because I mean, at the end of the day, what we can do whatever we want on the balloon side. It can be linear, it can be circular, but you have to account for just the pendulum, right? It's always going to be swinging, and sometimes it swings a lot, and sometimes it swings a little bit. It really just depends on how aerodynamic your faucet covers are, and there's not a lot you can really control on that front.
I understand.
But we can for sure build some form of antenna that's on the balloon that accounts for that, some circular, some wheel antenna, whatever.
I've got
But
wheels antennas from 800 megs to 10 gig.
And if I were to design a board with one of those little synthesizer chips, just to experiment with, I would probably, have some resistor I could turn to either dump it off to a connector or dump it off to just a like an inverted F antenna or some PCB, whatever, just for experimenting on that board. But I'm not an antenna expert. I barely claim to know how to spell RF, you know.
Hey, regarding the weight of the W1GHZ personal beacon board, I've got one I'm sitting here looking at, got 2 3/4 inch pipe caps on it, and it weighs 1.9 ounces. And the one for 10 gig would be less than that.
That's not bad at all.
So it would take an antenna and some sort of LO and keying circuit for it. You could probably keep that at well under 500 grams.
So one of the things in terms of an LO, and shame on me if I can't find it here. So this right here is an ST Micro dev board. In here is an STM32 WL33. This is an integrated ARM Cortex M0 processor with a radio, all on the same IC. It's like a 48-pin quad flat pack. Quad flat pack. And I would love to find a way to use something like this in that context just to reduce weight. You know, because if I don't have to go out and buy a separate radio IC and all this and that, if I can just run it off of that STM32, I'd be a happy camper. But that's not a today problem. That's a tomorrow or next month or next year, you know, engineering desire. But it is encouraging, though, that one board was only a couple of ounces there. With
Well, what we're talking about here is not even a radio, just an oscillator.
Yeah.
Just an oscillator with a multiplier and a way to turn it on and off.
Okay.
You could call it a radio. It's transmitting on a certain frequency, but you don't have to have an SDR or anything to start with.
Just jamming an oscillator into an antenna and calling it a day, huh?
Yeah, turn it on and off or modulate it like Kent said.
Some of the Houston balloon guys used to take a 28 or 29 megahertz oscillator, you know, not the crystal, but the full-on oscillator, and they would just connect it to a dipole, and they'd feed it with a 555 timer and like an LM35 temp sensor, and they called it a fireball because it had the root, it had the third harmonic, and it had, you know, just harmonics everywhere, and it was a really good thing to figure out altitude in a very primitive way, because you could kind of know, well, this many beeps means that it's this temperature, and you know, you could figure out altitude loosely from that temperature. I thought that was pretty cool. They've since stopped doing that because it actually is exceedingly illegal when you bother to read the FCC, you know, Part 97, but kind of fun that they did that back in the day. But anyway, that's all I've got, but I just want y'all as a group to kind of conspire and think about what would be fun to do, you know, above 432 megahertz from a balloon. You know, we're planning to do launches on a fairly regular basis. Things will probably calm down when it gets cold outside, because the cold weather does come with a very active jet stream that will push our landing site out toward like Tyler or Longview or whatever, and we're not really set up to chase that far. So we'll probably have a 6-month hiatus starting around November. But we plan on having another 2 or 3 launches between now and then, and we'll for sure kick things back off again next spring. So yeah, just keep us in mind. You know, we want more experimental payloads. As Chip said, the cameras, the tracking, the crossband repeating, all that cool stuff, but we've got that down to a science now, and we'd like to see some of the more interesting payloads on board. So that's all I've got.
When you look for weird ideas, I'll give you one in your weird idea moment.
Oh, you're muted. I see you talking, but the mute button.
Yeah, there you go. Sorry. Reason how guys in microwaves use, one of the things you horse race is how well you hear the beacons. And having a good beacon that you can rely on, as you know, is a way to check out your receiver. But I'll tell you something that was one of my sort of weird ideas of the moment, because there's so much cool computer technology. I don't really understand why there aren't remote reporting beacons, meaning you'd have something that would be a transfer and receiver both, and in your balloon situation, I think it'd be cool if you had, as you launch the payload, a wideband receiver that could evaluate signals coming in and repeat back signal strengths.
Yeah.
That way, guys could even sort of horse race on the deal, right?
Sure.
You both see the targets, and they have something that would tell you back what it sees in the moment. That has RF advantage, and particularly the idea that multipath and all of these weird propagation things like What if there's a big weird cloud between here and the balloon? What's that do? And does everybody see it the same way? Because right now, locally, when Jim goes out and is roaming around, there's a lot of exploration of things like, if we all aim in a certain direction, will we get heard better? And the balloon, because it can be active now, both to answer back. To me, that's a whole aspect that hadn't been embraced, at least not recently. Weird idea.
How I would actually implement that is pretty straightforward. You know, we've got this WeNet data link, right? 115.2 kbaud. And with Raspberry Pis, you know, a Pi 5 being so small and so powerful these days, we could easily run an FFT on the balloon and downlink the results of that FFT so you can then do your own post analysis to see the SNR on your carrier, etc. You know, and if we combine that with the beacon, you know, beacon's on 10 seconds and then we're listening and running the FFT for another 10 seconds and just alternate, you know, so a way to collect that data while also still providing the bidirectional goal there.
Just thinking that that'd be a way you might actually engage some guys that might not otherwise be involved. Is to say, how loud am I in the balloon today? And the novelty things, because I'm all about embrace even some of the old guys that don't understand all the ones and zeros, that'd be me, is if it had a voice that talked back to you and said, this is how loud I hear this guy. That kind of thing. Where's the novelty part of it?
Yeah, definitely a lot to think about. But I kind of like the group sentiment of step one being let's get a 10 gig beacon in the air, you know, and then we can start working on this as a phase two project.
And the environmentals of that, because at 10 gigs, you can't do quite the same things because of the radical temperature change and other stuff.
Yeah.
Thanks for your talk. I appreciate it. Good job.
Glad to be here. Jim, I'm going to turn it back to you. I think I'm about out of things to talk about.
Hello, Jim.
Yeah, I don't even see Jim on the
No, I'm coming on.
I do have a Central States announcement I'd like to make. For those of you who might be interested in our Chambers Award, we've had no nominations for a Chambers Award thus far this year. So if you want to look at the people who are attending and want to consider someone, let me know.
And do you have that list?
You can go to centralstates.org and you can get a list of the people who have registered. We vastly prefer to give the award to somebody who's actually there.
Okay. All right. So let's finish up here. I want to talk about phishing and scam emails. Be aware. We have some phishing schemes that are coming to us in the email. Here's one of them. Just use common sense. When we get to July, this is where we are right now. Go to Central States VHF Society in Lincoln a couple of weeks from now. In August, we have a MAD day at the 2nd. Another NTMS August Zoom meetings on the 9th. Proceeds on the 12th. First leg of the 10 gig and up contest. 2.3 gigahertz and up EME. September. Second, we have microwave activity day. On the 9th. EME test 13th and 14th, 52 1296. Then 20 and to the 22nd, part 2 of the contest. Here's the standing at three old business.
Hey, Jim, one thing for August 2nd and 3rd weekend, that's also our Mad Day, but I didn't see it get mentioned unless I'm blinked. The 222 and up distance contest is that weekend as well.
What's the date, Scott?
August 2nd and 3rd. Okay. And I'm going to guess that it probably starts at 1800 UTC on the 2nd.
That's an important contest, so I'll update this. So here's our routine. To the business meeting. Is there any old business?
I wasn't at the last meeting.
So no.
Repeat.
I said I was not at the last meeting, so no. Sir.
Thanks, Eric. Or remind you of the budget. Here are all the bullet points. Wes, you need to correct me if I've got these wrong.
Well, I can tell you that it's already been announced that everything postal postage wise went up on July 13th, and that includes boxes. I just don't know how much the box will be for next year.
Toughest box, we had 146. That's going to go up, right?
Yes.
Okay. Just need your $20 annual dues. Please support the club.
Currently, we are at 29 paid members for this year.
You need a few more.
Yeah, that's about the break-even point. Not quite, but close.
Thank you, Wes. Looking for a motion to adjourn.
So
I'll make a motion.
You, Al, second.
Second.
Thank you for the second. Thanks, everyone. Have a great weekend. We'll talk to you later. Thank you, Bob. See you later.
Send me through, Jim.
7:30.
We're going to say anything about the rain scatter or no?
Yeah.
Or another time?
Well, I think it's for later. There's new features on what Andy Flowers has done. Let's go there next time.
Sounds good.
Thanks, David.
Thank you. Bye.
Bye-bye.